close your eyes if you wish. Breathe with the rhythm of ancient stellar winds and drift with me through the galaxy we call home. The galaxy built from wreckage. The Milky Way may feel like a permanent, stable home, a fixed address in the cosmos where humanity has always resided. But this perception is an illusion, a trick of our brief lives measured against cosmic time. Our galaxy is not a pristine, unchanging structure. It is built from wreckage, from the scattered remains of smaller galaxies that wandered too close and were consumed. Over billions of years, the Milky Way has acted as a gravitational predator, drawing in dwarf galaxies, unraveling them with tidal forces, and scattering their stars like breadcrumbs into long, delicate streams that wrap around our galactic disk. These stellar streams are everywhere once you know how to look for them. Ghostly ribbons tracing the paths of galaxies that no longer exist as coherent structures. Right now, at this very moment, the Sagittarius dwarf galaxy is being slowly, relentlessly pulled apart. Its stars are being stripped away, absorbed into the greater structure of the Milky Way. If you could watch this process in accelerated time, you would see it as a kind of cosmic dissolution, the dwarf galaxy gradually fading like a watercolor painting in rain, its essence bleeding into the surrounding canvas. And this is not the end of such encounters. Far off in the night sky, visible to telescopes as a faint smudge of light, the Andromeda Galaxy, our nearest large galactic neighbor, is drifting steadily closer. The distance between us shrinks by about 110 kilometers every second, an approach so gradual that measured against a human lifetime, it seems frozen in place. But the universe measures time differently than we do. In approximately 4.5 billion years, these two great spirals will merge in what scientists poetically call a galactic collision. Despite the violent imagery that phrase conjures, the reality will be far more subtle. Stars are separated by such vast distances that direct collisions between them are almost impossibly rare. Instead, the galaxies will interpenetrate, their shapes warping and stretching as gravity works its patient magic. Spiral arms will be torn and reformed. Tidal tails, long streamers of stars, will curl outward into space like cosmic ribbons. The supermassive black holes at each galaxy's center may spiral together over hundreds of millions of years before finally merging in a cataclysm that will send ripples through space-time itself. After billions of years of this slow, elegant dance, the two galaxies will settle into a single, larger elliptical system. This future galaxy already has a name in some circles: Milky. It will be a new world, a new cosmic environment, though whether any life will remain to witness it is uncertain. Our sun will have entered its red giant phase by then, likely consuming the inner planets and rendering Earth uninhabitable long before the galactic merger is complete. Even galaxies, it seems, are not eternal. They evolve, collide, consume one another, and begin again. The universe practices a form of cosmic recycling on scales that dwarf our comprehension, constantly making and remaking itself through gravity's endless choreography. Stars older than their home. Here is a truth that borders on paradox. Some stars in the Milky Way are older than the Milky Way itself. Not every star that currently calls our galaxy home was born within its bounds. Some stars, particularly those drifting in long, tilted orbits through the galactic halo, appear to have formed even before the Milky Way had fully taken shape. These are the halo stars, ancient and metal-poor, moving through the galaxy's outskirts like elder spirits from a time before structure, before order. Astronomers believe these stars originated in smaller, primordial galaxies, the building blocks that merged together to form what we now know as the Milky Way. Their chemical fingerprints reveal their ancient heritage. They contain almost no heavy elements, the metals that later generations of stars would forge in their cores and scatter through supernova. This near absence of heavy elements tells us these stars were born shortly after the Big Bang itself, in a universe that was younger, wilder, and still learning to become what it is. They formed when hydrogen and helium, the primordial elements created in the first minutes after the universe began, were nearly all that existed. Each subsequent stellar generation has enriched the cosmic environment with heavier elements: carbon, oxygen, iron, gold. But these ancient wanderers remain chemically pure, time capsules from the universe's infancy. They move slowly and high above the galactic plane, following orbits that seem to ignore the spiral structure that dominates the galaxy's middle layers. In their light, we see a universe that existed before most of what we know took form. They are living fossils, their ancient photons carrying stories from an era when the cosmos was still finding its way, still experimenting with the fundamental structures that would become galaxies, stars, and eventually, consciousness itself. The endless motion of home. Our solar system, with its familiar sun and planets, does not sit still in space. Even as you rest here now, you are moving at tremendous speed. The entire solar system orbits the center of the Milky Way at over 828,000 kilometers per hour, more than 230 kilometers every single second. It's a velocity so extreme, it defies ordinary comprehension. At that speed, you could circle Earth's equator in less than 3 minutes. And yet, despite this incredible velocity, it takes approximately 225 million years to complete just one orbit around the galaxy. This vast circuit is called a galactic year, and it reveals the truly staggering scale of our cosmic home. In all of Earth's history, we've completed only about 20 orbits since the solar system formed roughly 4.6 billion years ago. Think about that for a moment. When the first dinosaurs appeared on Earth, our solar system occupied a completely different position in the galaxy. The star patterns visible in their skies would have been subtly different from ours. The stars we see as our celestial neighbors today weren't always nearby, and they won't remain so forever. Everything is in motion, quietly, slowly, endlessly. Even as you sleep tonight, the Earth continues its daily rotation. The moon circles our planet in its monthly dance, and the entire solar system, carrying with it every human who has ever lived, sweeps forward through a galaxy that itself is moving through space, following currents of dark matter and the gravitational pull of other structures in the universe. We exist in nested layers of motion, spinning on a planet, orbiting a star, circling a galaxy, moving through a local group of galaxies, drifting through a galactic supercluster. At every scale, motion is the rule, not the exception. Stillness is an illusion born of our limited perspective and brief lifespans. This is one of the deep truths that astronomy teaches us. We are not standing on solid ground beneath a fixed sky. We are sailors on a cosmic ocean, moving through currents we're only beginning to understand, following paths shaped by forces both visible and invisible, always in motion, never truly still, a structure still growing. Although the Milky Way is ancient, over 13 billion years old, formed when the universe itself was still young, it is not finished. Even now, at this very moment, it continues to grow, to gather material, to evolve. It accumulates gas from the intergalactic medium, those vast, nearly empty spaces between galaxies that nonetheless contain thin wisps of hydrogen and helium. It captures stars from dwarf galaxies that drift too close, gravitationally bound and slowly absorbed. It draws in streams of dark matter that feed its invisible halo. This growth doesn't happen like a living organism, with cells dividing and tissues expanding. It happens like a gravitational sculpture, deepening and elaborating its structure over time. Some of this growth occurs quietly, through gentle infall of material from surrounding space. Clouds of gas settling into the disk, condensing, cooling, eventually forming new generations of stars. Other times, growth comes with dramatic disruption. Satellite galaxies are torn apart by tidal forces, their stars scattered across the sky in long streams that wrap around the Milky Way like gossamer threads. These streams are visible to modern surveys, delicate arcs of stars that trace the death throes of smaller galaxies, their final legacy becoming part of our galactic structure. The galaxy you inhabit today is not the same one that existed when dinosaurs walked the Earth, and the Milky Way your distant descendants might know. If humanity survives, and spreads beyond this single planet. Could be larger still, stitched together from the ruins of 1,000 smaller worlds, its structure enriched by the accumulated heritage of countless stellar populations. This ongoing growth is a reminder that galaxies are not static monuments. They are dynamic, evolving entities, shaped by gravity and time into structures of almost impossible complexity. The Milky Way is still writing its story, still gathering the material that will determine its future form. The mystery of spiral arms. It seems like something we should know with certainty. How many spiral arms does the Milky Way have? It's our own galaxy, after all, our cosmic neighborhood. Yet this seemingly simple question remains surprisingly difficult to answer. From our position deep inside the disk, embedded among billions of stars, it's extraordinarily challenging to see the whole structure. Dust clouds obscure distant regions, blocking our view like fog in a forest. Stars blur together at great distances, overlapping and merging in our telescopes. For decades, astronomers believed there were 4 major spiral arms sweeping out from the galactic center. More recent observations have suggested maybe fewer, or perhaps that the arms twist and split in ways more complex than earlier models predicted. Some arms seem to fade into fragments as they extend outward. Others wrap around unexpectedly, refusing to follow the clean logarithmic spirals that grace simplified diagrams. The structure appears more organic than geometric, shaped by forces that don't always produce neat, symmetric patterns. The Milky Way may not be a perfect pinwheel at all, but rather a living, layered swirl of stars and gas, shaped by forces we still don't fully understand. Bars, density waves, gravitational interactions with satellite galaxies, the influence of dark matter. All these factors conspire to create a structure that's far more intricate and irregular than the tidy spirals we often see in artistic renderings. This uncertainty about even basic structural features of our own galaxy is humbling. It reminds us that despite our technological achievements and scientific advances, we remain embedded observers trying to understand a system from within. Imagine trying to map the shape of a forest while standing in its deepest heart, unable to rise above the canopy, and you'll begin to understand the challenge astronomers face in mapping the Milky Way's true structure. Rogue stars, the galaxy's exiles. Most stars drift calmly through the galaxy, following predictable orbits shaped by the gravitational pull of all the mass around them. But a rare few are flung outward at astonishing speeds. Velocities so extreme they can escape the Milky Way entirely, becoming intergalactic wanderers. These are hypervelocity stars, cosmic outcasts traveling at over 1 million kilometers per hour. Some are the remnants of binary star systems that wandered too close to the supermassive black hole at the galaxy's center. In these encounters, gravity plays a brutal game. One star falls inward, captured by the black hole's immense pull and likely torn apart. The other star receives the energy from this interaction, slingshot outward at tremendous speed, hurled into the dark like a stone from a cosmic catapult. These rogue stars travel alone, far from the galactic plane, their paths carrying them beyond the spiral arms, beyond the halo, into the vast intergalactic voids between galaxies. They are like glowing comets with no possibility of return, sentenced to eternal exile from the gravitational community that birthed them. They remind us that even in a galaxy bound together by gravity, that most fundamental and inescapable force, there are moments of violent release, quiet expulsions that send stars flying into the intergalactic night, carrying with them perhaps planets, perhaps the frozen remnants of worlds that once knew different skies. These hypervelocity stars raise profound questions. If they harbor planets, what would it be like to exist in such a system? To look up at night and see not the familiar band of the Milky Way, but the vast darkness of intergalactic space, with only distant galaxies as points of light? Would such isolation breed a different kind of consciousness, one more aware of the fundamental solitude that underlies all existence in the universe? The Andromeda encounter. High above the horizon on autumn evenings, visible even to the naked eye from dark locations, lies a faint smudge of light. This is the Andromeda Galaxy, a spiral much like our own, lying over 2.5 million light-years away. Its light, traveling toward us at the speed of light, takes 2.5 million years to reach our eyes. When you look at Andromeda, you're seeing it as it appeared when our ancestors were just beginning to walk upright on Earth's savannas. And yet, despite this vast distance, Andromeda is moving steadily toward us at about 110 kilometers per second. This approach is not random drift, but gravitational destiny. In approximately 4.5 billion years, the Milky Way and Andromeda will collide. It won't be violent in the way we typically imagine collisions. Stars are spaced so far apart relative to their size that direct impacts are almost impossible. Even as two galaxies interpenetrate, the probability of any single star colliding with another remains vanishingly small. Space is mostly emptiness, even in the crowded heart of a galaxy. But while stars won't crash together, their gravity will reshape both galaxies dramatically. The orderly spirals will be warped into long, stretching arcs. Tidal tails will curl outward, streams of stars pulled by uneven gravitational forces. Gas clouds will collide and compress, triggering intense bursts of star formation. Stellar nurseries igniting across the merger zone, creating brilliant blue-white stars that live fast and die young. The supermassive black holes at the center of each galaxy, millions of times more massive than the Sun, will spiral toward each other over hundreds of millions of years. Their eventual merger will release tremendous energy in the form of gravitational waves, ripples in space-time itself that will propagate outward at light speed, carrying the news of this cosmic marriage to the far reaches of the universe. After billions of years of gravitational chaos and gradual settling, the two galaxies will merge into a single, larger system. Likely an elliptical galaxy, its organized spiral structure replaced by a more spherical distribution of stars. This new galaxy will be quieter, older, most of its gas consumed or expelled during the merger, its era of vigorous star formation winding down. It will be a slow, elegant dance, played out over timescales that dwarf civilizations and species. The future of our cosmic home, written across the stars in the language of gravity and motion, backward orbits, signatures of ancient mergers. Most stars in the Milky Way orbit the galactic center in the same general direction, following the overall rotation established when the galaxy first formed. This preferred direction creates the spiral structure we observe, with stars and gas flowing through density waves that trigger ongoing star formation. But not all stars follow these rules. Some stars, especially in the outer halo, move in retrograde, orbiting opposite to the galaxy's main rotation. These contrary wanderers spin against the cosmic current, like salmon swimming upstream. These backward-moving stars didn't originate here. They likely were born in dwarf galaxies that were later absorbed by the Milky Way. Their reversed motion is a quiet signature of their foreign origin, a gravitational accent that reveals they came from elsewhere. The galaxy carries old memories in its motion, stories of ancient mergers and cosmic encounters, preserved not in light or chemistry, but in the slow, patient turning of stars against the stream. By mapping the orbits of these retrograde stars, astronomers can reconstruct the history of past collisions. Each absorbed galaxy leaves its mark in the orbital characteristics of its donated stars. It's like archaeological excavation, but instead of digging through layers of Earth, astronomers analyze the three-dimensional movements of stars, reading the galaxy's history in the patterns of motion written across the sky. The Gaia-Enceladus merger, reshaping the ancient galaxy. Over billions of years, the Milky Way has consumed not just dwarf galaxies, but substantial systems that profoundly shaped its structure. Astronomers have identified several of these ancient mergers by carefully analyzing stellar motion, chemical composition, and spatial distribution. The stars from these absorbed galaxies didn't vanish. They became part of our halo, disk, and stellar streams, their heritage preserved in subtle ways. One especially significant event, called the Gaia-Enceladus merger, or sometimes the Gaia sausage, occurred approximately 8 to 10 billion years ago. This wasn't a minor dwarf galaxy drifting too close. It was a substantial system, perhaps a quarter of the Milky Way's mass at that time. When it collided with our galaxy, the impact was profound. This merger added enormous numbers of stars to the Milky Way, particularly to the stellar halo and the thick disk. It may have fundamentally reshaped the early structure of our galaxy, heating the disk, puffing it up, and creating much of the thick disk population we observe today. The collision would have triggered intense bursts of star formation, lighting up both galaxies with brilliant blue-white stars. The evidence for this ancient cataclysm remained hidden until recently, when the European Space Agency's Gaia mission mapped the precise positions and velocities of over 1 billion stars with unprecedented accuracy. In that data, astronomers discovered a population of stars with unusual orbits, highly elongated ellipses stretching far from the galactic plane. Their chemical compositions matched, suggesting a common origin. Their ages clustered around 10 billion years. These were the remnants of Gaia Enceladus, its stars now fully integrated into the Milky Way, but still carrying the signature of their violent past in their orbital characteristics. The discovery revealed that our galaxy is not a pristine spiral born in isolation. It is a composite structure, built from quiet collisions and violent mergers, stitched together from the remains of many smaller worlds over billions of years. This realization has profound implications. It means the history of the Milky Way is more turbulent, more dynamic than previously understood. It suggests our galaxy grew primarily through merger and accretion, rather than peaceful accumulation of gas. And it raises the question, how many other ancient mergers remain to be discovered in the motions and chemistry of stars, their stories written in gravitational memory, elemental fingerprints, reading stellar histories? Every star carries within its light a unique chemical fingerprint, a pattern of elements imprinted at birth that remains largely unchanged throughout its life. These spectral signatures are like genetic codes, revealing not just what the star is made of, but where and when it formed, what materials were available in its natal cloud, and what prior generations of stars had contributed to that environment. By studying these chemical fingerprints, astronomers can trace a star's history with remarkable precision. Some stars are rich in heavy elements: iron, calcium, oxygen, magnesium, suggesting they formed in dense, metal-rich regions where many previous generations of stars had already lived and died, enriching the surrounding gas with the products of nuclear fusion and supernova explosions. Others are nearly pure hydrogen and helium, chemically pristine survivors from the universe's earliest epochs. These metal-poor stars formed when the cosmos was still young, before stellar alchemy had had time to seed space with heavier elements. Their composition reflects the primordial mix created in the Big Bang itself, with only traces of heavier elements from the first supernovae. These chemical differences allow scientists to group stars into families, populations with shared origins. They can identify stars that form together in the same molecular cloud, even if those stars are now scattered across the galaxy. They can uncover ancient mergers by finding groups of stars with similar unusual compositions and orbital characteristics, suggesting they came from the same absorbed dwarf galaxy. In this way, chemistry becomes a kind of time machine. It lets astronomers read a star's past like a poem written in light. Each absorption line in its spectrum a word, each element a verse, the entire pattern a story, reaching back billions of years to the conditions that existed when the star first ignited. The implications extend beyond pure astronomy. By mapping the chemical evolution of the galaxy, how metal content has increased over time and varies with location, scientists can reconstruct the history of star formation, trace the paths of galactic winds that transport enriched material between regions, and understand how environments like our own solar system acquired the heavy elements necessary for forming rocky planets and, eventually, life. Stellar streams, ribbons of galactic memory, across the sky, barely visible but unmistakable when mapped with precision instruments, stretch thin ribbons of stars in graceful arcs and curves. These are stellar streams, the remnants of smaller galaxies and globular clusters that wandered too close to the Milky Way and were gravitationally shredded. As these smaller systems orbit through the Milky Way's gravitational field, they experience tidal forces, the same forces that raise tides on Earth, but operating on galactic scales. The side of the dwarf galaxy or cluster closer to the Milky Way feels stronger gravitational pull than the far side. Over many orbits, this difference in pull stretches the system along its orbital path. Stars are gradually peeled away, first from the outer edges, then deeper into the structure. Over hundreds of millions of years, the entire system can be completely disrupted. Its stars spread into a long, delicate stream that traces its former orbital path. These streams wrap around the galaxy like ghostly halos, some diving toward the galactic center, others arcing far into the outer halo. Each stream is evidence of a past collision, a quiet merger that added to the Milky Way's mass and complexity. The streams are not chaotic tangles but organized structures, their stars moving on similar orbits because they came from the same disrupted parent system. By mapping these streams and tracing their paths backward, astronomers can determine where the original galaxy or cluster was located, how massive it was, even approximately when the disruption occurred. The galaxy, like a tree, carries the rings of its past in every thread of light. These stellar streams are the growth rings of galactic evolution, visible markers of the Milky Way's history of consumption and growth. They reveal that our galaxy is not an isolated island, but part of an ongoing process of hierarchical structure formation. Smaller structures merging to form larger ones, a process that began shortly after the Big Bang and continues today. The most famous stream is associated with the Sagittarius dwarf galaxy, which is currently being torn apart by the Milky Way's gravity. This stream wraps entirely around our galaxy, its stars spread through a full circuit. When astronomers first discovered it, they realized we're seeing a galaxy in the act of being consumed, a process that will take many more orbits to complete, but one that's inexorably reducing Sagittarius from an independent galaxy to a scattered stream of orphaned stars. The warped disk, a galaxy in motion, Lexi. Our galaxy doesn't lie flat like a perfect spiral in textbook diagrams. The Milky Way's disk is warped, bending upward on one side and downward on the other, forming a subtle S-curve when viewed edge-on. This graceful wave extends across vast distances, most pronounced in the outer regions where the disk thins and galactic gravity weakens. This warp was invisible to us for a long time. Visible light observations couldn't reveal it clearly because we're embedded within the structure, and dust obscures our view of the most distant regions. The warp became apparent only when radio telescopes mapped the distribution of neutral hydrogen gas, which extends far beyond the visible stars and traces the disk's true shape. The discovery raised immediate questions. What causes this warping? Several mechanisms might contribute. The gravitational influence of satellite galaxies, particularly the Magellanic Clouds. Tugging on the Milky Way's edges could create asymmetric distortions. Clumps or streams of dark matter passing through or near the disk might bend the structure from below or above. Past collisions could have set up oscillations that persist for billions of years, the disk still settling from ancient impacts. The warp reveals that even seemingly stable galactic disks are never fully still. Over time, they bend, flex, and respond to forces both internal and external. From a distance, the Milky Way might look like it's dancing slowly through space, its edges rippling like the hem of a twirling skirt. This dynamic character extends beyond simple warping. The disk also displays other asymmetries and peculiarities. One side appears slightly thicker than the other. The star formation rate varies between regions in ways not fully explained. The spiral arms don't match perfectly between opposite sides of the galaxy. These irregularities are not flaws, but rather signatures of the Milky Way's complex history and ongoing evolution. They remind us that real galaxies, shaped by messy processes over billions of years, rarely conform to idealized symmetric models. The beauty of the galaxy lies partly in these imperfections, these wrinkles and waves that tell stories of gravitational interactions and cosmic encounters. Dark matter, the galaxy's hidden scaffolding. By all conventional logic, examining only what we can see and measure directly, The Milky Way should not exist in its current form, based on the visible matter. Stars, dust, gas. The outer edges of the galaxy are spinning far too fast. According to Newton's laws, they should be flung into space, scattered like water droplets from a spinning wheel, and yet they remain, bound in orderly rotation. This paradox forced astronomers to confront an uncomfortable reality. Most of what holds the galaxy together cannot be seen. It doesn't emit light, doesn't reflect radiation, doesn't absorb passing photons. It interacts with ordinary matter only through gravity. This mysterious substance is called dark matter, and it outweighs all the visible stars, planets, dust, and gas in the galaxy by perhaps 5 to 1. It forms an enormous halo surrounding and interpenetrating the visible disk, its gravitational influence extending far beyond the furthest stars. We don't know what dark matter is made of. It's not ordinary matter, not protons, neutrons, and electrons arranged in atoms. It might be exotic particles predicted by extensions of the standard model of particle physics. WIMPs, weakly interacting massive particles, axions, sterile neutrinos. Or it might be something entirely unanticipated, a form of matter governed by physics we haven't yet discovered. Despite this profound ignorance about its nature, we know dark matter is there through its gravitational effects. It shapes the rotation curves of galaxies, holds galaxy clusters together, bends light through gravitational lensing, and leaves subtle imprints in the cosmic microwave background radiation from the early universe. The Milky Way's dark matter halo likely extends several 100,000 light-years from the galactic center, dwarfing the visible disk. This invisible scaffolding determines the galaxy's total mass, shapes its gravitational potential, and provides the foundation upon which the visible structure rests. Without dark matter, the galaxy would fly apart. With it, everything holds together in the patterns we observe. It is perhaps the greatest mystery in modern astronomy. This invisible majority that makes up most of the universe's mass yet remains completely undetected except through gravitational inference. Dozens of experiments around the world are searching for dark matter particles, hoping to detect the incredibly rare interactions that might occur when a dark matter particle passes through ordinary matter. So far, despite decades of increasingly sensitive searches, dark matter has remained stubbornly undetected through any means except gravity. This absence of detection doesn't disprove dark matter's existence. The particles might simply interact too weakly with ordinary matter to be caught, even by our most sensitive instruments. But it does highlight how much of the universe remains mysterious, how much of what fills space and shapes cosmic structure lies beyond our current ability to observe or understand. You can see only a fraction. Under a clear, dark sky, far from city lights, away from the glow of human civilization, you might see a few thousand stars with your naked eye. On an exceptional night from an exceptional location, perhaps 5,000 or 6,000 at most. To the human eye, this seems like an ocean of light, a sky crowded with stellar brilliance, but it's barely a droplet from the cosmic ocean. The Milky Way contains over 100 billion stars. Recent estimates suggest perhaps 200 to 400 billion. Most are hidden from view, made invisible by distance, faintness, or the thick curtains of dust that drape across large swathes of the galactic disk. Those few thousand visible stars represent approximately 0.003% of the galaxy's total stellar population. The pale streak of the Milky Way that crosses dark skies on moonless nights. That luminous band that has inspired wonder since humanity first looked up, is just the innermost whisper of the whole, the densest projection of the disk as seen from our embedded perspective. We live surrounded by a colossal river of starlight, an immense structure containing billions of suns, trillions of planets, uncountable worlds and moons. And yet almost all of it remains invisible to us, too distant to resolve, too faint to detect, hidden behind veils of interstellar dust, or simply below the threshold of what our eyes can perceive. This invisibility isn't just a limitation of human vision. Even our most powerful telescopes can observe only a fraction of the galaxy's contents. Much of the Milky Way is hidden in darkness, not because it doesn't emit light, but because that light is blocked before it reaches us. The galactic center, for instance, is completely obscured in visible light by intervening dust clouds. We can observe it only in infrared, radio, and X-ray wavelengths that penetrate the dust. This profound incompleteness of our view means we're still discovering fundamental features of our own galaxy. New structures, new stellar populations, new insights into the Milky Way's shape and history emerge regularly as technology advances and surveys become more complete. We are, in a sense, still mapping our own neighborhood, still learning the basic geography of home. The galaxy we inhabit is vastly larger, more complex, more populated than the tiny fraction we can directly perceive. This gap between what exists and what we can see humbles us, reminding us that for all our scientific advances, we remain embedded observers with limited perspective, trying to understand an immense structure from within. Sagittarius A, the silent conductor. At the very center of the Milky Way, hidden behind vast curtains of interstellar dust, lies an enormous black hole, a singular point of gravity so intense that not even light can escape its pull. This cosmic monster bears the designation Sagittarius A, pronounced Sagittarius A star, named for its position in the constellation Sagittarius as seen from Earth. Sagittarius A var is more than 4 million times the mass of our Sun, yet it occupies a space smaller than the orbit of Mercury. Imagine compressing 4 million suns into a region you could cross in a few light minutes. The density is beyond comprehension, the gravitational field so warped that space-time itself curves back upon itself at the event horizon, that boundary beyond which nothing, not matter, not light, not information itself, can return. We cannot see the black hole directly. By its very nature, it emits no light. But we've watched nearby stars whip around this invisible anchor at tremendous speeds, tracing elliptical orbits through apparently empty space. These stellar orbits reveal the presence of the black hole as clearly as watching birds circle reveals an invisible tower. The stars move so fast at closest approach, some reaching several percent of light speed, that they experience measurable relativistic effects, their light redshifted by the intense gravitational field. Sometimes gas and dust fall inward toward the event horizon. As this material spirals inward, friction heats it to millions of degrees, causing it to flare with X-rays and other high-energy radiation before making its final plunge into oblivion. These flares are brief and irregular, giving us glimpses of the feeding behavior of this gravitational predator. For now, Sagittarius A sleeps relatively quietly. It is not actively consuming large amounts of material, not blazing with the furious radiation of an active galactic nucleus. But long ago, in the galaxy's distant past, it may have burned like a quasar, one of the brightest objects in the universe, lighting up the galactic core from within, visible across billions of light-years of space. Evidence for this past activity comes from enormous structures called the Fermi bubbles, which we'll explore shortly. These gamma-ray emitting lobes extending above and below the galactic center may be the remnants of a massive outburst from Sagittarius A, an era when the black hole consumed material voraciously and ejected tremendous energies perpendicular to the disk. The black hole serves as the silent conductor of the Milky Way's heart, its gravity shaping the orbits of millions of stars in the central bulge, its presence felt across thousands of light-years. Stars in the innermost light-year orbit in mere decades, while those farther out take millennia to complete their circuits. All move to the rhythm set by this invisible maestro, bound in a gravitational dance that has continued for billions of years. There is something both terrifying and sublime about Sagittarius A. It represents the ultimate gravitational endpoint, a place where matter and energy are removed from the visible universe. And yet, it also represents order, the stable center around which an entire galaxy organizes itself. In this paradox, we glimpse something profound about the universe, that destruction and creation, chaos and order, often exist as complementary faces of the same cosmic processes, the peanut-shaped heart. When astronomers turned their most sophisticated instruments toward the galactic center, mapping not just positions, but three-dimensional structure, they discovered something unexpected, the central bulge, that dense concentration of stars surrounding the galactic core, is not a smooth, round ball. Instead, it has a strange, elongated geometry. Seen from certain angles, it resembles a peanut shell. From others, an hourglass twisted through space. This peculiar shape swells in the middle and narrows at the ends, a three-dimensional structure that defies simple description. The bulge is thick through its equator, but thinner toward its poles, creating a boxy or X-shaped appearance when viewed edge-on. This strange geometry likely formed from the galaxy's central bar, a dense stripe of stars that rotate slowly through the galactic core, distinct from the spiral arms that dominate the outer disk. Bars are common features in spiral galaxies. Perhaps 2/3 of all spirals show some degree of bar structure. They form naturally when stellar orbits in the inner galaxy become aligned, creating a rotating concentration of stars and gas. Over time, gravitational interactions cause this bar to buckle and puff upward, creating vertical structure. Stars in certain orbits get scattered above and below the galactic plane, while others become more concentrated along the bar's length. The cumulative effect, built up over billions of years of orbital mechanics, creates the complex three-dimensional shape we observe. These inner structures are sculpted by gravity, by billions of years of orbital evolution, by the accumulated rhythm of stellar motion. Nothing in the galactic center is simple or two-dimensional. We live in a spiral galaxy, but its heart is full of baroque complexity. Not flat or clean, but intricate and alive with motion. The central bar itself rotates at a different speed than the stars in the disk around it, creating a dynamic relationship between inner and outer galactic regions. This differential rotation helps drive the spiral arm structure, channels gas toward the center, potentially feeding the black hole, and influences star formation patterns throughout the inner galaxy. Understanding these central structures required painstaking observations, primarily in infrared wavelengths that can penetrate the obscuring dust. The detailed mapping revealed a galactic core far more complex than earlier, simpler models suggested. A reminder that the universe rarely conforms to our neat theoretical predictions, instead presenting us with beautiful complications that demand ever more sophisticated understanding. Stellar nurseries, where light begins. The Milky Way's spiral arms are not simply made of stars, fixed and permanent. They are woven from the birthplaces of stars. Vast clouds of hydrogen, dust, and complex molecules drifting through the galaxy, waiting for the trigger that will cause them to collapse and ignite. These molecular clouds are enormous beyond comprehension, spanning hundreds of light years across, containing enough material to form thousands or even millions of suns. They drift through space, cold and dark, their temperatures hovering just a few degrees above absolute zero, that theoretical point where all atomic motion ceases. When these clouds pass through the spiral arms, regions of higher density where gravity compresses material, or when they're struck by shock waves from nearby supernova, their delicate equilibrium is disturbed. Regions within the cloud begin to collapse under their own gravity, growing denser, warmer, beginning the slow journey towards star formation. As a collapsing region contracts, it heats up. Conservation of angular momentum causes it to spin faster, flattening into a disk. At the center, where material accumulates most densely, temperatures and pressures climb. The collapse continues over hundreds of thousands of years, until finally, when the core reaches about 10 million degrees Kelvin, hydrogen fusion ignites. A star is born. But birth is just the beginning. The ultraviolet light from these new stars ionizes the surrounding gas, causing it to glow in characteristic colors. Hydrogen emission producing rosy reds, oxygen creating blues and greens. These stellar nurseries become visible as emission nebulae, their radiant colors painting the spiral arms and illuminating the curves of the galaxy with quiet fire. The most massive young stars, blue giants burning fiercely, live only a few million years before exploding as supernovae. These explosions compress nearby clouds, triggering new generations of star formation in an ongoing cycle. Each burst of creation traces out the spiral structure, lighting up the arms with successive generations of brilliant young stars. Every star, even our Sun, was born from one of these cloudy cradles long ago. The Sun formed about 4.6 billion years ago in a stellar nursery that no longer exists as a cohesive structure. Its sibling stars, born from the same collapsing cloud, have long since scattered across the galaxy, most now impossible to identify among billions of similar stars. These nurseries are the galaxy's wombs, the quiet, hidden places where the future begins in darkness and cold, tucked within curtains of shadow and molecular gas. They are the foundation of the galaxy's ongoing renewal, the source of fresh stellar populations that replace the old stars gradually dying, ensuring the Milky Way remains vibrant and luminous despite its ancient age. The halo, memory at the edges, beyond the flat spiral disk extending into three-dimensional space in all directions, lies something far more diffuse and mysterious: the galactic halo. This vast spherical structure surrounds the entire visible galaxy like an enormous, ghostly bubble. The halo contains ancient stars, globular clusters, and staggering amounts of dark matter. Though nearly invisible, this outer region may hold the majority of the Milky Way's mass. Not in stars, which are spread thin across huge volumes, but in the dark matter, whose gravitational influence binds everything together. The stars of the halo are different from their disk cousins. They're generally older, often exceeding 10 billion years in age, formed in the galaxy's earliest epochs. They're metal poor, containing few heavy elements, born before many generations of stellar nuclear synthesis had enriched the galactic environment. And they move on highly eccentric orbits, long ellipses that carry them far from the galactic plane, sometimes plunging through the disk, but spending most of their time in the vast spaces above and below. These halo stars orbit in slow, graceful arcs that rarely intersect with the disk. A halo star might take hundreds of millions of years to complete a single orbit, moving through regions of space so empty that encounters with other stars are virtually impossible. They are the galaxy's hermits, ancient wanderers drifting through near-empty space. The halo also preserves the remnants of ancient galactic mergers. Stellar streams wrap through this region, thin ribbons of stars torn from smaller galaxies that were absorbed billions of years ago. Some streams form complete loops around the galaxy. Others stretch in long arcs, slowly dispersing over time. These streams are fossils, the preserved remains of the Milky Way's growth through merger and accretion. Globular clusters populate the halo as well, compact spheres of hundreds of thousands to millions of stars, gravitationally bound into tight, beautiful configurations. These clusters orbit the galactic center like moths circling a distant flame, their orbits carrying them through the halo in long, looping paths. The halo is the galaxy's outer memory, a quiet and dim region where the most ancient stellar populations survive, where the evidence of past collisions slowly circles, where dark matter dominates and visible matter becomes sparse. It reminds us that the visible disk, for all its prominence and beauty, represents only a fraction of the galaxy's true extent. From within the disk, we rarely think about the halo. It contributes little to the night sky's appearance, its stars too faint and scattered to draw attention. But it shapes everything. Its gravitational mass influences disk dynamics. Its ancient stars carry information about the galaxy's formation. Its structure traces the invisible dark matter distribution that ultimately determines the Milky Way's fate. Globular clusters, time capsules in orbit. Among the oldest structures in the galaxy, globular clusters represent stellar populations that have remained intact since the universe's early epochs. These dense, spherical collections of stars are spectacular even in small telescopes, appearing as fuzzy balls of light that resolve into seas of individual stars under higher magnification. Each cluster contains hundreds of thousands to millions of stars, packed into a volume typically only tens to hundreds of light years across. This creates stellar densities far higher than the solar neighborhood. In a globular cluster's core, stars might be separated by mere light weeks or light days, rather than the light years that separate stars in the disk. These clusters are incredibly stable, some more than 12 billion years old. They've survived since the galaxy's youth, maintaining their structure despite countless orbits through the galactic gravitational field. Their longevity and isolation have preserved ancient stellar populations, making them invaluable for studying stellar evolution and the early universe. The stars within globular clusters are uniformly old and metal-poor. They contain almost none of the heavy elements that characterize younger stellar populations, suggesting they formed before the universe had time to create many elements heavier than helium. This chemical signature indicates formation shortly after the Big Bang, when the raw materials available for star formation consisted almost entirely of primordial hydrogen and helium. The Milky Way contains over 150 known globular clusters, though the actual number is likely higher. Some may be hidden behind the galactic bulge or obscured by dust. They orbit through the halo like a swarm of golden bees around the galactic center, their orbits highly elliptical, plunging periodically through the disk, but spending most of their time at great distances. These orbits are clues to their origins. Some clusters likely formed with the Milky Way itself, condensing from the same primordial gas cloud that would become our galaxy. Others may have been captured from dwarf galaxies during mergers, their parent systems long since dissolved while the clusters themselves remained gravitationally bound and intact. Globular clusters serve as time capsules, holding clues about galaxy formation, the early universe's conditions, and stellar evolution in metal-poor environments. They're also natural laboratories for studying stellar dynamics, the gravitational interactions between stars packed into relatively small volumes. Over billions of years, these interactions lead to mass segregation, with more massive stars sinking toward cluster centers, while lighter stars drift to the outskirts. These quiet, golden spheres drift patiently through the halo, glowing softly in the darkness, each one a preserved sample of the ancient cosmos, their ancient stars still shining with light that began its journey when the universe was young and the Milky Way was still learning what it would become. Differential rotation, the spiral's secret. Unlike a solid wheel rotating uniformly, the Milky Way displays differential rotation. Stars at different distances from the center orbit at different speeds. This creates one of the galaxy's most beautiful and complex features, the spiral arms themselves. In the inner regions, closer to the galactic center, where mass is concentrated, stars orbit relatively quickly. Moving outward, orbital velocities remain surprisingly constant, a fact that reveals the presence of dark matter, as we've discussed. But the key point is that stars don't move together as a rigid structure. They orbit independently, at speeds determined by the gravitational forces acting on them. This differential rotation means the galaxy doesn't spin like a solid disk. Instead, it behaves more like a fluid, with different regions moving at different rates. This creates shearing motions, regions where material moves past other material at different speeds. These shearing motions help generate and maintain the spiral arm structure through something called density wave theory. The arms aren't fixed trails of specific stars, but rather patterns. Regions of higher density that rotate through the galactic disk at their own speed, different from the stars themselves. Imagine a traffic jam on a circular highway. The jam itself moves slowly around the circle, but individual cars enter it, slow down briefly, then exit and speed up again. The traffic jam persists as a pattern, even though it's made of constantly changing cars. Similarly, spiral arms persist as density patterns, even though individual stars and gas clouds drift in and out of them. As stars, and especially gas clouds, enter a spiral arm, they slow down slightly, compressed by the gravitational potential of the density wave. This compression triggers star formation in molecular clouds, lighting up the arm with brilliant young blue stars. These massive stars live only a few million years before exploding, so they never drift far from where they formed. This is why spiral arms appear blue and bright. They're outlined by successive generations of short-lived, massive stars. Meanwhile, older stars continue their independent orbits, gradually drifting out of the spiral arms. The Sun, for instance, is currently between major spiral arms, located in the Orion Spur, a minor structure connecting larger arms. Over its 4.6 billion year lifetime, the Sun has drifted in and out of spiral arms multiple times as it orbits the galaxy. This differential rotation creates the illusion of structure and form from what is essentially chaos and independent motion. It's a beautiful example of emergent order. Large-scale patterns arising from the collective behavior of billions of independent objects, none of which knows about the overall structure they collectively create. The galaxy is not a clock with synchronized gears. It is a current, a flow, a dynamic system where order emerges from motion, where beauty arises from complexity, where patterns persist despite, or perhaps because of, constant change. We are drifting in this current, moving through patterns that shift and evolve on timescales both longer and shorter than human comprehension. Dark matter, the invisible majority. The Milky Way holds together because of something we cannot see, cannot touch, cannot directly detect through any means except its gravitational effects. This mystery has a name, dark matter. But naming it doesn't bring us closer to understanding what it actually is. By all conventional physics, the Milky Way should not exist in its current form. Stars in the outer regions orbit too fast, based on the visible mass. All the stars, dust and gas we can account for. They should be flung into space, the galaxy gradually dispersing into the void, and yet they remain, bound in stable orbits. The resolution to this paradox requires accepting that most of the galaxy's mass is invisible. Dark matter doesn't shine, doesn't reflect light, doesn't absorb radiation passing through it. It interacts with ordinary matter only through gravity, the weakest of the fundamental forces, but the one that operates over the largest distances. There is so much dark matter that it outweighs all the visible matter in the galaxy by perhaps 5 to 1, maybe more. It forms an enormous halo extending far beyond the visible disk. Its gravitational influence, the true determinant of the galaxy's rotation curve, its structure, its stability. We don't know what dark matter is made of. This is not a small gap in our knowledge. It's one of the most profound mysteries in modern physics. Dark matter is clearly not ordinary matter, not composed of protons, neutrons, and electrons arranged into atoms. It must be something else entirely. Candidates include exotic particles, predicted by various extensions of the standard model of particle physics. WIMPs, weakly interacting massive particles, were long favored, though decades of increasingly sensitive searches have failed to detect them. Axions, incredibly light particles that barely interact with anything, remain possible. Sterile neutrinos, primordial black holes, modifications to gravity itself. All these and more have been proposed. Despite this profound uncertainty about its nature, we know dark matter exists through multiple lines of evidence. Galaxy rotation curves like the Milky Way's, the dynamics of galaxy clusters, where the visible matter is insufficient to explain the observed motions. Gravitational lensing, where dark matter's gravity bends light from background galaxies. The cosmic microwave background, where dark matter's influence is imprinted in the subtle variations of ancient radiation. Dark matter is the invisible scaffolding that holds everything together. Without it, galaxies would fly apart, galaxy clusters would disperse, the large-scale structure of the universe couldn't have formed. It is fundamental to cosmic architecture, yet it remains almost completely mysterious. The Milky Way swims in a sea of dark matter, particles passing through you, through Earth, through the Sun, every second. Trillions of dark matter particles stream through your body continuously, interacting so weakly that they pass through without leaving any trace, without depositing any energy, without any effect whatsoever except their cumulative gravitational pull. This should humble us profoundly. The universe is made primarily of something we don't understand. Most of reality is invisible to us, detectable only through its gravitational influence. We are like investigators examining a crime scene where most of the evidence is invisible. We can see the effects, the disturbances left behind, but the thing itself remains hidden. Yet this mystery also excites. Somewhere in dark matter's nature lies physics beyond our current understanding. Discovering what it is, detecting it directly, understanding its properties, incorporating it into our physical theories, would represent one of the greatest scientific achievements in history, fundamentally expanding our understanding of reality itself. For now, it remains the galaxy's greatest secret, the invisible majority that determines everything, yet reveals nothing about itself except through gravity's patient pull. Supernovae, the galaxy's storms. When massive stars reach the end of their lives, having fused elements in their cores from hydrogen to helium to carbon to oxygen and beyond, they die in spectacular fashion. The core, now composed of iron, can no longer generate energy through fusion. Deprived of the outward pressure that balanced gravity throughout the star's life, the core collapses catastrophically. In less than a second, a region the size of Earth compresses to a ball perhaps 20 kilometers across. The density becomes so extreme that protons and electrons are forced together, creating neutrons and releasing enormous numbers of neutrinos. The core rebounds, sending a shockwave outward that tears through the star's outer layers. This is a supernova, an explosion so powerful it can briefly outshine an entire galaxy. For a few weeks, a single dying star emits more light than hundreds of billions of normal stars combined. The explosion releases as much energy in those brief weeks as the Sun will emit over its entire 10 billion year lifetime. These explosions don't just end lives, they create. The shockwaves from supernovae ripple through the interstellar medium, compressing nearby molecular clouds and triggering new waves of star formation. The compression creates regions of higher density that begin to collapse under their own gravity, eventually forming the next generation of stars. Even more importantly, supernovae forge and disperse heavy elements. Elements heavier than iron cannot be created in normal stellar fusion. They require the extreme conditions of supernova explosions: gold, platinum, uranium, thorium. These and many other heavy elements are created primarily in supernova and similar catastrophic events. These newly forged elements are blasted into space, mixing with the interstellar medium. They enrich the galactic environment, becoming available for incorporation into new stars, planets, and eventually life. Every heavy atom in your body, the calcium in your bones, the iron in your blood, the gold in any jewelry you wear, was forged in a supernova explosion billions of years ago, scattered into space, and eventually incorporated into the molecular cloud that formed our solar system. In this way, supernovae act like storms within the galactic ecosystem. They stir, they fertilize, they reshape everything around them. They are moments of violent chaos, destruction on scales difficult to comprehend, yet they're also necessary. Without them, the universe would remain composed almost entirely of hydrogen and helium. No rocky planets could form, no complex chemistry could arise, no life as we know it could exist. The galaxy breathes with these explosions. They occur somewhere in the Milky Way every few decades on average, each one releasing tremendous energy, each one contributing to the ongoing cycle of stellar birth, life, death, and rebirth that has continued for billions of years. We owe our existence to supernova violence. The atoms that make us possible were forged in stellar furnaces and scattered by catastrophic explosions. We are, quite literally, the children of dead stars, made from their scattered remains, living on a planet assembled from supernova debris, looking up at a sky where similar dramas continue to unfold. Dust, the veil and the cradle. The Milky Way is full of light we cannot see, hidden behind veils of interstellar dust. This dust, microscopic grains of carbon, silicates and ice, each grain smaller than the particles in smoke, weaves through the galaxy in clouds and tendrils, obscuring vast regions of space. In visible light, these dust clouds appear as dark patches against the starry background, regions where stars seem to vanish, where the Milky Way's luminous band is broken by what appear to be gaps and rifts. Early astronomers, not understanding what they were seeing, sometimes called these dark nebulae, thinking them regions devoid of stars. But the dust doesn't mark empty space, It marks the opposite: regions where material is concentrated, where molecular clouds gather, where star formation occurs. Behind the veil, hidden from visible light, stellar nurseries bustle with activity. Infrared telescopes revolutionized our understanding of these regions. Infrared light, with wavelengths longer than visible light, can penetrate dust clouds that completely block visible light. When astronomers turned infrared telescopes toward dark nebulae, they found them filled with young stars, protostars still forming, entire stellar populations invisible to conventional telescopes. What appears as darkness, invisible light, reveals itself as a cradle of light when viewed at the right wavelengths. The dust, though it hides, is part of the creative process. Dust grains absorb stellar radiation, helping cool the surrounding gas. This cooling is essential for gravitational collapse. Hot gas resists compression, but cold gas can collapse into dense cores that eventually become stars. Dust grains also serve as surfaces where chemical reactions can occur, building up complex molecules that would be difficult to form in the gas phase. Some of the organic compounds detected in molecular clouds, including the building blocks of amino acids and sugars, form on dust grain surfaces. The dust itself is interesting. These microscopic particles are created in the atmospheres of dying stars, particularly red giants and supernovae. As stars age and swell, becoming red giants, they shed their outer layers in stellar winds. These winds contain material processed in the star's interior: carbon, oxygen, silicon, iron. That condenses into solid grains as it cools. These grains drift through space, accumulating in molecular clouds, eventually becoming incorporated into new stars and planets. Some of the dust grains in the molecular cloud that formed our solar system may have been captured unchanged, preserved in comets and asteroids. Scientists have found pre-solar grains, dust particles older than the solar system, identifiable by their unusual isotopic compositions, in primitive meteorites. These tiny survivors carry stories from previous stellar generations, physical remnants of stars that died before our sun was born. Interstellar dust is thus both veil and cradle. It hides the galaxy's star-forming regions from our direct view, yet it enables the very processes it obscures. What seems like emptiness or darkness is often the beginning of something bright, the protective cocoon within which new suns ignite, wrapped in curtains of shadow until they grow strong enough to blow away their dusty wombs and shine freely. The galactic recycling system. Stars are not permanent fixtures, despite how they appear in our brief lifetimes. They live, burn, and die, and in dying, they return their material to the galaxy. This cosmic recycling has been operating since the first stars formed, billions of years ago, and it continues today. Supernovae spread heavy elements in spectacular explosions, but they're not the only mechanism. Red giants, stars that have exhausted the hydrogen in their cores and swelled to enormous size, shed their outer layers in stellar winds. Over thousands or millions of years, these winds carry significant fractions of the star's mass back into space. Planetary nebulae, misnamed, having nothing to do with planets, represent a particularly beautiful phase of this recycling. When a sun-like star finally exhausts its fuel, it ejects its outer envelope, creating an expanding shell of gas illuminated by the hot stellar core left behind. These nebulae glow in intricate patterns, shells and rings of gas spreading outward at tens of kilometers per second, gradually mixing with the interstellar medium. This material, enriched by nuclear fusion in stellar cores, joins the interstellar medium where it cools, condenses, and eventually forms new stars, planets, and moons. Each stellar generation incorporates elements forged by previous generations. Over billions of years, the galactic environment has grown progressively richer in heavy elements, transforming from the nearly pure hydrogen and helium of the early universe to the chemically complex medium we observe today. Every atom in your body has passed through this cycle, likely multiple times. The hydrogen in your water molecules is primordial, created in the Big Bang itself, but the oxygen was forged in massive stars that exploded as supernovae. The carbon in your organic molecules, the nitrogen in your DNA, the calcium in your bones. All were created in stellar cores, scattered into space, cooled and condensed into the molecular cloud that formed the Sun, incorporated into the protoplanetary disk, assembled into planetesimals, accreted into Earth, and eventually gathered into the biochemistry that became you. You are made of stardust. This is not metaphor, but literal truth. The atoms composing your body are ancient, cycled through multiple stellar generations, carriers of a history that stretches back billions of years to the galaxy's earliest epochs. The Milky Way is not a static stage where unchanging stars shine eternally. It is a great engine of renewal, breathing in time with stellar evolution. Stars are born from the cold molecular clouds. They live for millions or billions of years, fusing light elements into heavier ones. They die, returning their processed material to space, and the cycle begins again, each iteration adding to the chemical complexity, making possible ever more intricate structures, planets, atmospheres, oceans, life, consciousness. The galaxy makes, unmakes, and begins again in an endless rhythm that has continued for most of cosmic history. We exist at a particular moment in this cycle, in an era when enough stellar generations have lived and died to enrich the galaxy with heavy elements necessary for rocky planets and complex chemistry. Yet early enough that stars still form in abundance, that the galaxy remains vibrant and alive. This recycling system connects everything. The iron in hemoglobin molecules that carry oxygen through your blood came from a supernova. The gold in any jewelry you wear was forged in an even more violent event. The collision of neutron stars, the silicon in computer chips, the oxygen in the air you breathe, the nitrogen in your proteins, all cycled through multiple stellar generations before becoming part of you. In this sense, you are not separate from the cosmos. You are the cosmos, a temporary arrangement of atoms that have existed for billions of years and will continue existing in other forms long after your current configuration dissolves. The galaxy has been breathing these atoms in and out for eons, and you represent one brief moment in that endless respiration. Metal-poor stars. Messages from the dawn. In astronomy, metals means something different than in everyday language. Astronomers call any element heavier than helium a metal. So, oxygen, carbon, nitrogen, iron, gold, everything beyond the two lightest elements. This nomenclature arose historically and persists despite its potential confusion. The earliest stars in the universe had almost no metals because they formed before previous stellar generations could forge and scatter heavy elements. Today, astronomers seek out metal-poor stars throughout the galaxy, particularly in the halo, because these ancient objects preserve the chemical conditions of the early universe. These stars are faint, easily overlooked among brighter stellar populations, but they're invaluable for understanding cosmic history. By analyzing their composition through spectroscopy, breaking their light into component wavelengths, and identifying absorption lines from various elements, astronomers can reconstruct the chemical state of the gas from which these stars formed. The most metal-poor stars have iron abundances less than 1/10,000th that of the Sun. Their atmospheres are almost pure hydrogen and helium, with only traces of heavier elements. These traces reveal important information about the very first stars, which may have been massive, short-lived, and different in character from stars forming today. Those first stars, called Population 3, never yet directly observed, likely formed from completely pristine gas with exactly zero heavy elements. When they exploded as supernovae, they seeded their surroundings with the first metals, creating gas slightly enriched in carbon, oxygen, and other fusion products. The most metal-poor stars we observe today probably formed from this slightly enriched gas, making them second-generation stars carrying information about what the first generation was like, by studying the patterns of elemental abundances in these ancient survivors. Which elements are present, in what ratios, with what peculiarities? Astronomers can constrain theories about those first stars. Some metal-poor stars show unusual abundance patterns, suggesting they formed from gas enriched by specific types of supernovae. Others show evidence of being enriched by pair instability supernovae, a particular type of explosion possible only in the most massive first-generation stars. These ancient objects are scattered throughout the halo, slowly orbiting the galactic center on long ellipses, drifting through nearly empty space like messages in bottles, their light carrying information from an era when the universe was young and almost everything was different. They are fossils made of light, each one a physical sample of ancient conditions, their atmospheric compositions preserving the primordial past. In studying them, we peer back through billions of years to the period just after the Big Bang, before galaxies had matured, before the Milky Way itself had taken shape, to a time when the universe was learning to make heavier elements and assemble them into structures. These stars move slowly and high above the galactic plane, having avoided the gravitational interactions that would have circularized their orbits over time. They are the galaxy's elders, silent witnesses to its formation and the long, slow shaping of what we now call home. In their spectral lines, we read chapters from a book written before most of cosmic history unfolded. A text in starlight, patient and enduring, waiting billions of years for observers capable of understanding the story it tells. The Wanderers, stars far from home. A star's birthplace doesn't define its ultimate destiny. Over cosmic time, many stars drift far from their natal clouds, pushed by gravitational interactions, orbital resonances, or the slow influence of spiral arm passage. The galaxy is not a static arrangement of fixed positions, but a dynamic system where objects migrate, sometimes dramatically. Some stars are ejected at high speeds, flung across the disk or into the halo by gravitational encounters. A close pass by a massive molecular cloud can accelerate a star significantly. Three-body interactions, where three stars pass close enough that their mutual gravitational interactions become complex and chaotic, can result in one star being ejected at high velocity while the other two form a bound binary system. Others migrate more gradually, their orbits evolving over millions of years due to subtle gravitational perturbations. These migrations can be radial, moving inward or outward from their formation radius, or they can involve changes in orbital eccentricity or inclination. Even our Sun is not where it began. Tracing the Sun's orbit backward suggests it formed farther inward than its current position, perhaps a few thousand light years closer to the galactic center. Over 4.6 billion years, gradual gravitational interactions have nudged it outward to its current location in the Orion Spur. This orbital migration has important implications for the solar system's history. The Sun has drifted through different galactic environments, spending time in denser regions where supernova might have been more common, passing through spiral arms multiple times where radiation levels would have been higher, experiencing different cosmic ray fluxes at different epochs. Some researchers have speculated whether this orbital motion might correlate with patterns in Earth's geological or biological history, whether passing through spiral arms might trigger ice ages or mass extinctions through increased cosmic ray exposure or gravitational disturbances from nearby stars. The evidence remains inconclusive, but the question illustrates how the solar system's galactic journey might have influenced conditions on Earth. Tracing stellar paths reveals a Milky Way far more dynamic than early models suggested. Stars don't remain in their birth neighborhoods, but drift extensively over their lifetimes. The stellar populations we observe at any given galactic radius represent a mix of stars born locally and migrants from other regions, all blended together by billions of years of orbital evolution. Home for a star is temporary, a brief way station in a journey that covers thousands of light years and billions of years. We think of stars as fixed, permanent anchors in the sky, but on appropriate timescales, they're nomads, drifting through a galaxy that's itself in constant motion, never truly still, always flowing like a cosmic river whose currents carry everything forward through time and space. A Goldilocks region among the stars, just as Earth orbits in a habitable zone around the Sun. Not too hot, not too cold, but just right for liquid water and life. The Milky Way may possess its own galactic habitable zone, a region where conditions favor the development of complex life. This zone exists between two extremes. Too close to the galactic center and conditions become hazardous. The stellar density increases dramatically, raising the probability of close stellar encounters that could disrupt planetary systems. Supernova explosions occur more frequently in these star-rich environments, bathing nearby systems in sterilizing radiation. The supermassive black hole at the center creates intense gravitational chaos, its tidal forces and occasional violent outbursts making the innermost regions inhospitable. Too far from the center, and different problems emerge. The outer galaxy is metal-poor. It contains fewer heavy elements because star formation has been less vigorous there, meaning fewer stellar generations have enriched the environment. Rocky planets like Earth require substantial amounts of elements heavier than hydrogen and helium, silicon, iron, magnesium, oxygen in various forms. In the outer galaxy, these elements are scarce, making Earth-like planets harder to form. The outer regions are also more sparse, with greater distances between stars. This isolation might seem beneficial, fewer supernova threats, but it also means less stellar recycling, slower chemical enrichment, and perhaps more vulnerability to intergalactic threats or gravitational disturbances from passing dark matter structures. Somewhere between these extremes lies a wide band where conditions are more favorable. Star density is moderate, enough nearby stars to ensure chemical enrichment through successive generations, but not so many that close encounters or frequent supernova become existential threats. Heavy elements are abundant, making rocky planet formation probable. The radiation environment, while never completely safe, is manageable. Earth lies within this zone, orbiting a quiet star in a relatively calm neighborhood, at a galactic radius where conditions have remained stable for billions of years. This positioning may not be coincidental. Perhaps life is common only in such regions, and we find ourselves here because these are the only places where observers like us can arise. The concept remains somewhat speculative. We don't yet know enough about the distribution of life in the galaxy to confirm whether such a zone exists, but the logic is compelling. Life as we know it requires stability over long timescales, chemical richness for building complex molecules, and protection from catastrophic radiation events. These requirements may naturally define a galactic region where complex life is most probable. Our location in this zone, if it exists, represents yet another layer of cosmic fortune. Not only does Earth orbit at the right distance from a stable star, but that star orbits at the right distance from the galactic center, in a region where heavy elements are available, but catastrophic events are rare enough to allow lifetime to develop. We exist in a nested series of Goldilocks zones, the right planet, orbiting the right star, located in the right part of the right galaxy, at the right epoch in cosmic history, when stars still form, but enough stellar generations have passed to create chemical complexity. Each layer represents a filter, a requirement that narrows the possibilities, but creates the conditions necessary for consciousness to arise and contemplate its own existence. This perspective should inspire both humility and wonder. Humility because our existence depends on an extraordinary confluence of favorable conditions at multiple scales. Wonder because despite all these requirements, we're here. The universe has produced at least one instance of matter organized into patterns complex enough to understand, however imperfectly, the cosmic story of which it's a part. The fluid arms, patterns in motion. The Milky Way's spiral arms might seem like permanent features, grand, sweeping structures carved into the galaxy's disk, fixed and eternal. But this perception misunderstands their true nature. The spiral arms are not made of particular stars locked in formation. They are patterns, density waves that ripple through the disk, compressing material as they pass. Stars drift into these arms, slow down briefly due to the increased gravitational pull, then drift out again on the other side. The spiral structure moves at a different speed than the stars themselves, typically slower, creating a differential rotation between the pattern and the material moving through it. This is analogous to a traffic jam on a highway. The jam itself moves slowly or remains stationary, but individual cars enter it from behind, decelerate as they move through it, then accelerate again upon exiting. The traffic jam persists as a pattern, even though it's constantly made of different cars. The jam has a quasi-permanent existence, despite being composed of transient elements. Similarly, spiral arms persist as long-lived density patterns despite being composed of constantly changing stellar populations. The pattern rotates at what's called the pattern speed, while stars orbit at different velocities depending on their distance from the galactic center. What makes the spiral arms visible is star formation. As giant molecular clouds pass through the density wave, they're compressed. This compression destabilizes the clouds, triggering gravitational collapse and initiating the formation of new stars. The most massive of these stars, blue giants and supergiants, are incredibly luminous but short-lived, surviving only a few million years. These bright, young stars outline the spiral arms because they don't live long enough to drift far from where they formed. They're born in the density wave, shine brilliantly for a brief time, then explode as supernovae while still within or near the spiral structure. Their blue light traces the arms, creating the dramatic spiral patterns visible in images of face-on galaxies. Older, longer-lived stars like the Sun pass through spiral arms multiple times during their lifetimes. Each passage might last several million years, brief compared to stellar lifespans, but long enough to potentially influence planetary systems passing through. The increased stellar density, higher supernova rate, and enhanced cosmic ray flux in spiral arms might represent periodic environmental challenges for any life existing in those systems. From a distance, the spiral structure looks like form and order, beautiful, geometric, almost intentional. From within, it's a dynamic pattern of shifting motion held together by gravity and time, never still, always flowing. The arms are not objects, but processes, not structures, but patterns that emerge from the collective behavior of billions of stars and gas clouds, each following its own orbit, but collectively creating something larger than themselves. This understanding transforms how we see the galaxy. We're not embedded in a static structure, but flowing through a dynamic pattern, drifting in and out of density waves, carried by gravitational currents we barely perceive. The Milky Way is less like a city with fixed streets and buildings, and more like a weather system, with currents and patterns that persist, but constantly evolve, stable in overall form, but fluid in detail. The cosmic symphony, invisible radiation, beyond visible light, the galaxy glows with more mysterious forms of energy, creating a multi-wavelength symphony that reveals aspects of reality invisible to human eyes. Cosmic rays, high-energy particles born in supernova remnants, active galactic nuclei, and other violent events, stream through space constantly, passing through your body every second of every day. These cosmic rays are mostly protons, and atomic nuclei accelerated to nearly the speed of light by shockwaves from exploding stars or magnetic fields near black holes. They carry tremendous energy, and when they strike atoms in Earth's atmosphere, they create cascades of secondary particles that shower down to the surface. Your body experiences thousands of cosmic ray hits every day, each particle passing through you in a fraction of a second, depositing tiny amounts of energy, occasionally causing mutations in DNA that your cellular repair mechanisms usually fix. These particles carry stories from across the galaxy, evidence of ancient supernovae, traces of distant acceleration mechanisms, messages written in high-energy particles rather than photons. X-rays shimmer from dying stars, neutron stars accreting material from binary companions, and the regions immediately surrounding black holes where infalling matter heats to millions of degrees. These X-rays paint a picture of the galaxy's most extreme environments, places where matter exists in states never found on Earth, where temperatures and densities exceed anything achievable in terrestrial laboratories. Gamma rays, the highest energy photons, trace the most violent events, supernova explosions, gamma-ray bursts, matter-antimatter annihilation, and decay of exotic particles. The Fermi Gamma Ray Space Telescope has revealed that the gamma-ray sky looks completely different from the visible light sky, with different sources dominating, different structures prominent. Radio waves drift through space from sources both natural and exotic. Neutral hydrogen emits characteristic 21 centimeter radiation, allowing radio telescopes to map the galaxy's gas distribution even through obscuring dust. Pulsars, rapidly rotating neutron stars, emit beams of radio waves that sweep across space like cosmic lighthouses, their pulses arriving with extraordinary regularity. Synchrotron radiation, created when electrons spiral through magnetic fields at relativistic speeds, produces radio emission from supernova remnants, active galactic nuclei, and regions of intense star formation. This radiation traces magnetic field structures, revealing the invisible threads of magnetism that permeate the galaxy. When you look at the night sky, you're seeing only a narrow band of the electromagnetic spectrum, the thin slice of wavelengths to which human eyes happen to be sensitive, determined by the properties of the star we orbit and the evolutionary history that shaped our vision. But the galaxy broadcasts across all wavelengths, from kilometer-long radio waves to gamma rays with wavelengths smaller than atomic nuclei. Each wavelength reveals different phenomena, different physics, different aspects of the cosmic story. The Milky Way hums with this invisible energy, a multispectral symphony playing constantly. Beneath the peaceful appearance of the night sky, the galaxy seethes with high-energy processes, magnetic turbulence, particle acceleration, and radiation flux that would be instantly lethal if not for Earth's protective atmosphere and magnetic field. This hidden cosmos reminds us how limited our direct perceptions are. The universe we see directly, the visible light cosmos of stars and galaxies, is only a small fraction of what exists. Most of reality operates at wavelengths we cannot perceive without technological assistance, in forms that would be completely invisible and unknown, if not for scientific instruments extending our senses beyond their evolutionary limits. The galaxy speaks in many voices, many frequencies, a hidden symphony in the dark that astronomy has learned to detect and translate into understanding. The Fermi bubbles, echoes of ancient violence. Stretching tens of thousands of light years above and below the galactic center are two vast, ghostly lobes of high-energy light, structures so large they dwarf most individual features of the galaxy. These are the Fermi bubbles, discovered only in 2010 by NASA's Fermi Gamma Ray Space Telescope, despite being enormous and relatively nearby. They glow in gamma rays, the highest energy photons, extending like twin balloons from the Milky Way's heart, their edges surprisingly sharp, suggesting a relatively sudden formation rather than gradual buildup. Each bubble spans about 25,000 light-years from the galactic plane, meaning the total structure is roughly 50,000 light-years tall, about half the diameter of the entire visible disk. No one is entirely certain what created them. The most likely explanations involve the supermassive black hole at the galactic center. Perhaps several million years ago, Sagittarius A experienced a period of intense accretion, consuming enormous amounts of gas and dust. During such feeding frenzies, active galactic nuclei can eject tremendous amounts of energy in jets perpendicular to the accretion disk. These jets, carrying energy equivalent to millions of supernovae, would have plowed through the interstellar medium above and below the disk, creating vast cavities filled with hot, gamma-ray emitting gas. The sharp edges of the bubbles might represent shock fronts where the expanding material encounters resistance from the surrounding medium. Alternatively, or additionally, the bubbles might result from intense star formation in the galactic center. Periods of starburst activity, when large numbers of massive stars form in a short time, create many supernovae in quick succession. These combined explosions could drive powerful winds out of the galactic center, again creating the observed structures. Whatever their origin, the Fermi bubbles represent evidence of dramatic past activity in what now appears to be a relatively quiet galactic core. They're reminders that the Milky Way has a history we cannot fully see, that the peaceful appearance of the modern galaxy may mask a more violent past. These enormous structures drift silently over the galaxy, invisible to human eyes, detectable only through sophisticated instruments sensitive to gamma-ray wavelengths. They are cosmic fossils, preserved evidence of events that occurred millions of years ago. Their signature still visible because the structures are so vast that light takes tens of thousands of years to cross them. When we observe the Fermi bubbles, we're seeing different parts of the structure as they appeared at different times. The near edge as it was recently, in cosmic terms, the far edge as it was 50,000 years ago. The structure exists in a kind of temporal blur, its full extent visible only because light's finite speed allows us to see across time as well as space. They are echoes of violence wrapped in radiance, drifting far above the stars we know, invisible markers of the Milky Way's capacity for dramatic change, reminders that the galaxy's current state is just one moment in a long dynamic history. Our quiet spur, a fortunate location. Our solar system doesn't occupy one of the Milky Way's grand spiral arms, not the Sagittarius arm, not the Perseus arm, not any of the major structures that dominate the galactic disk. Instead, we reside in a minor feature called the Orion Spur, also known as the Orion Arm or Local Arm, a relatively small structure connecting the larger arms. This spur is about 10,000 light-years long and roughly 3,500 light-years wide, significant on human scales but minor compared to the major spiral arms stretching tens of thousands of light-years. It's named for the Orion constellation because when we look toward Orion, we're looking along the length of this structure, seeing the stars that populate our local neighborhood. The Orion Spur is not especially dense, not particularly active in terms of star formation, not remarkable in any dramatic way. It's a cosmic suburb, a quiet lane between the busier highways of the major spiral arms. And this ordinariness might be precisely why we're here. In the calm between galactic highways, conditions are more stable. Massive supernovae are rarer because stellar density is lower. Radiation storms from nearby supernovae or active star-forming regions are less frequent. Close stellar encounters that might disrupt planetary systems are less common. Gravitational perturbations that might destabilize comets in the outer solar system, sending them plunging toward the inner system in potentially catastrophic impacts, occur less often. This quiet corner may have given life on Earth the time and stability it needed to emerge and evolve. Life requires continuity over immense timescales. Billions of years for single-celled organisms to evolve into complex multicellular life. Hundreds of millions more years for intelligence to arise. Such long-term stability might be difficult to achieve in denser, more active regions, where environmental disruptions occur more frequently. From the dramatic spiral arms, the galaxy appears radiant, active, turbulent with star formation and stellar death. But in this quiet spur, we found just enough peace, just enough stability, just enough protection from galactic-scale catastrophes for complexity to unfold, for evolution to operate over geological timescales, for consciousness to eventually arise and look back at the cosmos, wondering at its own existence. Our location represents yet another apparently fortunate circumstance. Not in the galactic center where chaos reigns, not in the outer wastes where heavy elements are scarce, not in the dense spiral arms where supernova rates are high, but in a minor structure where conditions have remained relatively benign for billions of years. Whether this is genuine fortune or selection, bias remains uncertain. Perhaps life arises only in such regions, meaning we necessarily find ourselves in this type of location, because these are the only places where observers can exist. Or perhaps life is more robust than we imagine, capable of surviving in many galactic environments, and our location is merely one of many possibilities. Either way, the Orion Spur has been our home for the entire history of life on Earth, a quiet eddy in the galactic current where complexity had time to develop, where intelligence had space to emerge, where beings capable of contemplating the cosmos could arise and begin asking questions about their place in the vast structure they inhabit. The central bar, a rotating bridge, when astronomers observe the galactic core in infrared wavelengths, light that can penetrate the obscuring dust-blocking visible light. They see not a perfect circular concentration of stars, but something more interesting. A thick, elongated bar crossing the middle of the galaxy, a kind of glowing bridge perhaps 27,000 light-years long. This central bar rotates slowly, taking about 100 million years to complete one rotation. It's not just a visual feature, but a dynamically important structure that shapes the inner galaxy's behavior. The bar's gravitational influence affects stellar orbits throughout the inner regions, creating complex resonances and orbital families. Bars form naturally in many spiral galaxies. Observations suggest that roughly 2/3 of nearby spirals show some degree of bar structure. They develop when stellar orbits in the inner galaxy become aligned, creating an elongated distribution of stars that rotates as a coherent structure, distinct from the spiral arms dominating the outer disk. Once formed, bars tend to be stable, persisting for billions of years. Their gravitational influence channels gas toward the galactic center, potentially feeding the central supermassive black hole and triggering nuclear star formation. This gas transport mechanism makes barred galaxies important laboratories for understanding how black holes grow and how central regions evolve. The bar also influences the spiral arm structure. The arms often appear to emerge from the ends of the bar, winding outward from those anchor points. The bar's rotation creates a different pattern speed than the spiral arms, leading to complex interactions between these different density patterns. For stars orbiting in the inner galaxy, the bar's gravity creates a potential field different from the simple, axially symmetric field of an unbarred disk. This leads to distinctive orbital families. Some stars follow paths aligned with the bar, orbiting along elongated ellipses, while others follow perpendicular paths, their orbits avoiding the bar's dense regions. The bar may also be responsible for the peanut-shaped or boxy appearance of the Milky Way's bulge. As bars evolve, they can buckle vertically due to instabilities, creating stars that move high above and below the galactic plane in the inner regions. This vertical puffing produces the three-dimensional structure observed in infrared surveys. Discovering the bar relatively recently, definitively established only in the 1990s, illustrates how much we're still learning about basic galactic structure. The bar was hidden from earlier observations by dust extinction and by our embedded perspective, which makes it difficult to see the galaxy's overall shape. Only with improved infrared capabilities and sophisticated modeling could astronomers confirm its existence and map its properties. The bar is not just a shape, but a dynamic engine, stirring gas, triggering star formation, feeding material to the black hole, and sculpting the galaxy's heart from within. It represents order emerging from chaos, a coherent structure arising from the collective motion of billions of stars, each following its own orbit, but together creating a pattern that influences everything around it. The local group, a galactic family. The Milky Way doesn't exist in isolation, floating alone through empty space. It belongs to a gravitationally bound collection of more than 50 galaxies known as the local group, a small cluster drifting together through the universe, each member influenced by all the others. The two largest members are the Milky Way and Andromeda, each a massive spiral galaxy with its own family of satellite galaxies. These two giants dominate the local group gravitationally, their combined mass determining the structure and evolution of the entire system. Scattered around these two large spirals are smaller galaxies of various types. Dwarf ellipticals, faint smudges of light containing relatively few stars. Dwarf spheroidals, even fainter systems so dominated by dark matter that they barely glow at all. Some contain perhaps 10,000 stars, making them as much dark matter halos that happen to contain a few stars as true galaxies in the traditional sense. Irregular dwarfs showing no particular structure, scattered collections of stars and gas that never organized into clear shapes. The Magellanic Clouds. The Large Magellanic Cloud and Small Magellanic Cloud are the Milky Way's most prominent satellites, visible to the naked eye from the southern hemisphere as detached pieces of the Milky Way. These are substantial dwarf galaxies, each containing billions of stars, orbiting our galaxy in a complex dance that may be pulling them apart through tidal forces. Andromeda has its own retinue of satellite galaxies, including M32 and M110, both visible in small telescopes near Andromeda's bright core. Additional faint dwarf satellites continue to be discovered around both the Milky Way and Andromeda as surveys become more sensitive and complete. The local group spans more than 10 million light-years, held together not by proximity alone, but by gravity. The galaxies within it are gravitationally bound, meaning their mutual gravitational attraction overcomes the expansion of space itself. While distant galaxies recede from us as the universe expands, local group members remain gravitationally linked, orbiting within a common potential well. This gravitational binding means the local group is a genuine physical structure, not just a convenient observational category. It represents a scale of cosmic organization intermediate between individual galaxies and galaxy clusters, a modest gathering of galaxies that share a common fate. Over time, many local group members will likely merge. The Milky Way and Andromeda are on a collision course. Some dwarf galaxies will be tidally disrupted and absorbed. Others may merge with each other. Billions of years from now, the local group might contain fewer, larger galaxies. Perhaps a single giant elliptical formed from the Milky Way-Andromeda merger, surrounded by a diminished population of surviving dwarfs. We are part of a family, quietly, widely spaced, but still linked by invisible threads of shared motion and mutual gravitational pull. The Milky Way's future is entangled with these neighboring galaxies. Their masses influence our galaxy's motion through space. Their gravitational tugs may create subtle effects in the outer Milky Way. And eventually, some will merge with our galaxy, their stars becoming part of a new, hybrid structure. This cosmic family represents another layer of context for understanding our place in the universe. We exist not just in a galaxy, but in a gravitationally bound system of galaxies, a local cosmic ecosystem where members interact and influence one another across millions of light-years of space. Gravitational bonds across the void, despite the vast separations between local group galaxies, measured in millions of light-years. These systems are not drifting apart. Many are actually moving slowly toward one another, their paths curved by mutual gravitational attraction. Gravity holds them in a kind of slow-motion ballet, elegant trajectories spanning millions of years. Some of the smallest galaxies orbit the Milky Way like moons, following looping paths that carry them around our galaxy over hundreds of millions or billions of years. With each passage, tidal forces stretch and pull at these dwarf galaxies. The most vulnerable ones, those that pass closest or have already been weakened by previous encounters, are gradually torn apart, their stars stripped away and distributed into long stellar streams. These streams wrap around the Milky Way, marking the paths of galaxies in various stages of dissolution. Some streams are recent and well-defined, easily traced in surveys. Others are ancient and dispersed. Their stars spread so widely that they're difficult to distinguish from the general halo population. Each represents a dwarf galaxy that came too close, paid the price for its proximity, and left behind these ghostly ribbons as its only memorial. Other local group members drift independently but remain gravitationally tethered, caught in the group's potential well without being bound to any specific large galaxy. These wanderers follow their own paths through the local group, their trajectories shaped by the combined gravitational influence of all the system's mass. Over cosmic time, this gravitational web leads to gradual consolidation. Galaxy groups like the local group tend to merge over billions of years, with smaller members accreted by larger ones, with the largest galaxies eventually merging into single, more massive systems. This hierarchical merging is fundamental to cosmic structure formation. Small systems merge to form larger ones, from the first tiny proto-galaxies in the early universe to the massive elliptical galaxies dominating rich galaxy clusters today. The local group represents our system caught in mid-process. It's not primordial. Many mergers have already occurred, creating the two large spirals from dozens of smaller predecessor galaxies. But it's not fully merged either. The final major merger, between the Milky Way and Andromeda, still lies billions of years in the future. This is not a static arrangement, but a gentle gathering of cosmic islands, drawn together by time, inertia, and gravity's patient pull. The local group is condensing, slowly but inexorably, toward a future where most of its members will have merged into a single massive galaxy, their individual identities lost, but their mass and stars preserved in a new configuration, layers within the disk. The Milky Way's disk appears flat from a distance, a thin plane of stars extending across thousands of light years. But up close, this apparent simplicity resolves into layered complexity. The disk is not uniform, but stratified, containing distinct stellar populations with different properties, ages, and kinematics. The thin disk is where we live. A relatively narrow layer, perhaps 1,000 light-years thick, containing young stars, open clusters, and active star-forming regions. This is the vibrant, active part of the galaxy, where most current star formation occurs, where massive, short-lived stars shine brilliantly before exploding, where spiral arms are outlined by successive generations of bright blue stars. Stars in the thin disk orbit on nearly circular paths close to the galactic plane. Their orbits are well ordered, all moving in roughly the same direction with relatively small vertical motions. This ordered behavior results from their formation in a settled, rotating disk where gas clouds orbit smoothly, transferring that ordered motion to the stars born from them. Above and below the thin disk lies the thick disk, a more diffuse layer extending perhaps 3,000 light-years from the galactic plane. Stars in the thick disk tend to be older, typically 8 to 12 billion years in age, with fewer heavy elements than thin disk stars. Their metallicity, the abundance of elements heavier than helium, averages about half that of the Sun, suggesting they formed earlier in galactic history, when the interstellar medium was less enriched. Thick disk stars move on more tilted and elliptical orbits, suggesting they formed under different conditions or were stirred by gravitational interactions that heated their orbits, scattering them above and below the plane. Their kinematics preserve evidence of the galaxy's more turbulent early history, when major mergers were more common and could disrupt stellar motions on large scales. The origin of the thick disk remains debated. It might have formed through gradual heating of thin disk stars, bypassing molecular clouds and spiral arms over billions of years. Alternatively, it might result from ancient mergers, stars from absorbed dwarf galaxies, or disrupted by major collisions like the Gaia-Enceladus event. Or it might represent stars that formed during a chaotic early epoch, when the galaxy was still settling from the violent conditions following its initial assembly. This vertical structure means the galaxy's disk is not a simple, uniform sheet, but a textured, layered composition shaped by billions of years of evolution. It's like sediments settled on the floor of a cosmic ocean, different layers representing different epochs, different conditions, different histories, all preserved in the spatial and kinematic distribution of stars. Moving through this disk, we pass through populations with different stories to tell. The young thin disk speaks of recent star formation, ongoing processes visible in real time. The old thick disk whispers of ancient conditions, early mergers, the galaxy's tumultuous youth. Together they create a three-dimensional fossil record, readable by those who know how to interpret stellar ages, compositions, and motions. Invisible currents through the cosmos. Though invisible to the eye and intangible to the touch, the Milky Way is laced with a vast magnetic field. An intricate web threading through the disk, rising into the halo, weaving through the interstellar medium like veins of energy through a cosmic body. This field is weak by earthly standards, thousands of times weaker than a refrigerator magnet. Yet over galactic distances, its influence becomes profound. Imagine these magnetic field lines as currents in an invisible ocean, flowing around stars, wrapping through spiral arms, connecting disparate regions across thousands of light years. They shape how cosmic rays travel. High-energy particles follow these magnetic threads, spiraling along field lines, bouncing between magnetic mirrors, creating tortuous paths through space rather than straight trajectories. The field influences how gas clouds collapse into stars. As clouds contract under gravity, magnetic field lines frozen into the plasma provide resistance, slowing the collapse, channeling material along particular directions. In some regions, magnetic support prevents collapse entirely, keeping clouds stable against gravitational contraction. In others, field lines thread through collapsing cores, potentially shaping the angular momentum distribution and influencing whether single stars or binary systems form. These magnetic structures align with spiral arms, forming arcs above the galactic plane, twisting into loops that defy simple explanation. Their complexity emerges from multiple sources: fields amplified by differential rotation as the galaxy spins, fields created by dynamo processes in stellar interiors and released through stellar winds, fields tangled and reorganized by supernova explosions and turbulent gas flows. Studying this magnetic architecture requires radio telescopes and careful analysis. Radio waves emitted by electrons spiraling in magnetic fields, synchrotron radiation, carry information about field strength and geometry. Polarized starlight passing through magnetized dust clouds reveals field orientation. Pulsar signals, delayed by different amounts depending on the magnetic field strength along their path to Earth, provide three-dimensional information about field structure. What emerges from these observations is astonishing complexity. The magnetic field is not uniform or simple, but intricate beyond early expectations. Local variations, coherent structures spanning thousands of light years, turbulent tangles on smaller scales, all coexist in a dynamic electromagnetic tapestry. The Milky Way does not just glow with light and mass, it breathes with magnetism, a subtle pulse running through its structure, invisible yet fundamental, shaping the behavior of charged particles, influencing star formation, connecting distant regions through invisible threads of electromagnetic force. Close your eyes for a moment and imagine these field lines surrounding you, passing through you. You exist within this magnetic structure, embedded in electromagnetic currents that span the galaxy. The field is too weak to feel, too subtle to detect without instruments, yet it's there, part of the hidden architecture that makes the galaxy what it is. The sea between stars. Between the stars lies more than emptiness, more than absence. The interstellar medium, a thin blend of gas, dust, and plasma, weaves through the Milky Way like an invisible sea, pervading the space we think of as empty. To the naked eye, this medium is mostly invisible, revealing itself only occasionally as glowing nebulae or dark clouds silhouetted against background stars. But when astronomers view it with radio and infrared telescopes, it reveals stunning complexity. The interstellar medium forms filaments stretching across light years, delicate threads of denser gas. It creates bubbles, vast cavities carved by stellar winds and supernova explosions, their edges glowing where shock waves compress the surrounding gas. It generates shock fronts where fast-moving material collides with slower regions, creating visible boundaries in space. Cold, dense molecular clouds float through this sea, islands of concentration where temperatures drop to barely 10 degrees above absolute zero. These clouds are star nurseries, the wombs from which new suns will eventually emerge. Around them, warmer neutral hydrogen extends in vast sheets, tracing the spiral arms and filling the space between. Hot, ionized plasma occupies the largest volumes. Gas heated to millions of degrees by supernova explosions, creating tenuous bubbles that can span thousands of light years. This hot gas glows in X-rays, invisible to optical telescopes, but brilliant to space-based X-ray observatories. It represents the most extreme phase of the interstellar medium, material energized by stellar death, expanding outward, gradually cooling as it mixes with cooler components. Supernova carve vast cavities in this medium, their blast waves pushing outward at thousands of kilometers per second, sweeping up surrounding gas into expanding shells. These shells eventually slow and fragment, but they leave lasting imprints. Hot interior regions that take millions of years to cool, dense shells where swept-up gas may eventually collapse to form new stars. Stellar winds sculpt the medium into shapes that ripple across light years. Young, massive stars blow powerful winds that clear regions around themselves, creating bubbles of hot gas. When many massive stars form together, their combined winds can create superbubbles hundreds of light years across, breaking through the galactic disk and venting hot gas into the halo. The space between stars is not a void, but a shifting web of matter and magnetism, a dynamic fabric from which galaxies evolve and life eventually begins. Temperature varies wildly across this medium, from millions of degrees in supernova remnants to barely 10 degrees in the densest molecular clouds. Density varies even more dramatically, from 1 atom per cubic centimeter in hot bubbles to millions of molecules per cubic centimeter in cloud cores. This is the quiet fabric on which the galaxy's drama unfolds. Stars are born from it, live within it, die back into it. Everything visible, planets, stars, nebulae, exists embedded in this invisible sea, shaped by it, contributing to it, part of an endless cycle of material flowing between different states, different temperatures, different densities. Breathe slowly and consider. The atoms you're breathing now were once part of this interstellar medium. They drifted through space as tenuous gas, gathered into a molecular cloud, collapsed into the protoplanetary disk around the forming sun, accreted into Earth, cycled through oceans and atmosphere and living things for billions of years, and now pass briefly through your lungs before returning to the air. You are not separate from this cosmic sea. You are made of it, temporarily organized into complexity, but fundamentally continuous with the material flowing between stars. The boundaries we perceive, between self and environment, between Earth and space, between living and non-living, are real but permeable, temporary configurations in an endless flow of matter through different states. Cosmic rays, the galaxies whisper in particles. Every second, high-energy particles stream through your body, mostly protons and atomic nuclei accelerated to nearly the speed of light, launched long ago by exploding stars or swept up in shockwaves around supernova remnants. These are cosmic rays, and they carry stories from across the galaxy. They travel close to the speed of light, bending through magnetic fields that thread the galaxy, bouncing off magnetic mirrors, following tortuous paths through space. Most originated in supernovae. The shockwaves from these explosions can accelerate particles to enormous energies through a process called Fermi acceleration, where particles bounce back and forth across the shock front, gaining energy with each crossing until they reach relativistic speeds. Others come from more exotic sources, particles accelerated near the event horizons of black holes, nuclei shattered in high-energy collisions between cosmic rays and interstellar atoms, perhaps even particles created in the decay of dark matter or other exotic physics beyond current understanding. When cosmic rays enter Earth's atmosphere, they collide with nitrogen and oxygen nuclei high above the surface. These collisions create showers of secondary particles, pions, muons, electrons, photons, cascading downward through the atmosphere. Some of these secondary particles reach the surface, passing through buildings, through rock, through your body. Most of the time, we don't notice them. Our bodies have evolved in this background radiation. Our cellular repair mechanisms adapted to fix the occasional DNA damage caused by cosmic ray hits. But the particles are there, constantly passing through, connecting you to the galaxy's most violent processes. Each cosmic ray that strikes you carries evidence of ancient supernova, traces of particle acceleration in extreme environments, messages from the violent heart of stellar death. They are whispers in particles rather than light, stories told in high-energy protons rather than photons. A different kind of cosmic communication that's been flowing through space for billions of years. Some cosmic rays have been traveling for millions of years, bouncing through the galaxy's magnetic fields, gradually diffusing outward from their sources. They map the magnetic field structure through their trajectories, creating a kind of particle echo that reveals invisible magnetic architectures. They influence the chemistry of molecular clouds, providing the ionization that drives certain chemical reactions. They may even influence Earth's climate in subtle ways, though this remains controversial. Even as you rest here now, the galaxy whispers to you in this silent language of particles, invisible, unfelt, but constant. Thousands of cosmic rays passing through you every minute, each one a messenger from the violent universe, each one carrying a fragment of energy released in some long-ago stellar catastrophe. The universe doesn't communicate only in light. It speaks in particles, in gravitational waves, in neutrinos, in magnetic fields. Multiple languages overlapping, multiple messages written in different forms of energy, all permeating space, all available to those who develop the instruments to listen. You exist, bathed in this invisible flux, embedded in energy flows that span the galaxy, touched constantly by particles that began their journeys in dying stars thousands of light years away. The separation between you and the cosmos is less than it appears. You are not isolated from galactic processes, but intimately connected to them, part of the same physical system, subject to the same forces, made of the same fundamental particles, following the same physical laws. The lopsided galaxy. Though many diagrams show the Milky Way as a neat, symmetric spiral with arms perfectly balanced on opposite sides, reality is messier, more interesting, more alive. The Milky Way is not perfectly balanced. It shows asymmetries at multiple scales, quirks and irregularities that reflect its complex history and ongoing evolution. One side of the disk appears thicker than the other. The scale height of stars varies between northern and southern galactic hemispheres in ways not fully explained by simple models. Some spiral arms are brighter, longer, or more curved than their counterparts on the opposite side. The warp in the outer disk is lopsided, bending more dramatically in some directions than others. Even the stellar sensor shows asymmetries. Star counts differ slightly between hemispheres, suggesting the disk's mass distribution isn't perfectly centered. Gas distributions show similar asymmetries, molecular clouds concentrated differently in different sectors. Hydrogen maps revealing uneven structures that don't mirror across the galactic center. These asymmetries likely arise from multiple causes. Gravitational interactions with satellite galaxies create uneven tidal forces, pulling more strongly on the near side than the far side, creating lopsided distortions. The Magellanic Clouds, orbiting in the southern galactic hemisphere, may be responsible for some of the observed north-south asymmetry, their gravity tugging the disk in particular directions. Past mergers could have introduced asymmetries that persist for billions of years. When the Gaia Enceladus dwarf galaxy collided with the Milky Way perhaps 8 to 10 billion years ago, it didn't hit perfectly symmetrically. The impact heated different parts of the disk unequally, scattered stars into the halo with different distributions on different sides, perhaps seeded density perturbations that still influence structure today. Dark matter distributions might be irregular, creating uneven gravitational potentials that manifest as visible asymmetries in the stellar distribution. Simulations suggest dark matter halos are rarely perfectly spherical or smooth. They contain substructure, clumps, streams from disrupted satellites. These irregularities in the dark matter could translate to irregularities in the visible matter distribution. These asymmetries remind us that galaxies, like living things, carry traces of their histories in their shapes. They are not manufactured to specification, not created according to perfect blueprints, but grown through complex processes over billions of years. Scars from collisions, wrinkles from gravitational interactions, quirks from uneven growth. All these imperfections give galaxies character and depth. Real beauty often lies in asymmetry, in the unique irregularities that distinguish one galaxy from another. The Milky Way is not less beautiful for being lopsided. If anything, its imperfections make it more interesting, more individual, a unique structure with its own particular history, written into every asymmetric feature. From a distance, these irregularities might be subtle, barely noticeable, but they're there, encoded in the distribution of stars and gas, waiting for precise observations to reveal them. Each asymmetry is a clue, a piece of evidence about past events or ongoing processes, part of the galaxy's story written in its structure. We live within this lopsided, imperfect structure, and that shapes our observations and our understanding. Our embedded perspective makes it difficult to perceive these large-scale asymmetries directly. We would need to view the galaxy from outside to see them clearly. Instead, We detect them through careful analysis of stellar distributions, gas kinematics, and comparison with simulated galaxies. The galaxy is not a perfect Platonic form, but a real, physical structure shaped by history, by chance, by the messy processes of gravitational interaction and merger and evolution. Its beauty lies not in perfection, but in the complex reality of what it actually is. A lopsided, warped, asymmetric spiral still growing, still changing, still being shaped by forces both internal and external. Ancient stars, survivors from the dawn, high above the galactic plane, drifting through the halo in long, slow orbits, astronomers have discovered stars that may be nearly as old as the universe itself. These ancient objects contain almost no heavy elements. Their atmospheres are nearly pure hydrogen and helium, the primordial elements created in the Big Bang. One such star likely formed over 13 billion years ago, long before the Milky Way had fully assembled into its current structure. It may have been born in one of the tiny protogalaxies that eventually merged to form our galaxy, or possibly in the very early phases of the Milky Way's formation, when the galaxy was still a chaotic, unorganized cloud of gas and dark matter. This star burns quietly now with a soft red glow, low in mass, perhaps 80% the mass of the Sun. Had it been more massive, it would have burned through its fuel billions of years ago and died. But small stars burn slowly, sipping their hydrogen fuel over tens of billions of years, allowing them to survive from the universe's youth to the present day. It is not just a star, it is a time capsule, a living relic from the universe's earliest dawn. In its spectrum, the pattern of absorption lines created as light passes through its atmosphere, we read a chemical composition that hasn't existed anywhere in quantity for over 13 billion years. The star contains less than 1/10,000th the iron content of the Sun, marking it as a product of an era before many stellar generations had enriched the cosmic environment. These survivors are incredibly rare. Most stars from the universe's first billion years were massive, burning brilliantly but briefly, exploding as supernovae long ago. The few small stars born in that era, the ones that could survive to the present, are scattered through the galactic halo, faint and difficult to find among billions of younger, brighter stars. When astronomers locate one, it's cause for excitement. Each ancient survivor provides a window into conditions in the early universe, a direct sample of primordial gas, evidence of what the cosmos was like before it had time to fully transform itself through stellar alchemy. These stars move slowly through the halo, their orbits carrying them far from the galactic plane, through regions of space so empty that they may go millions of years without passing near another star. They are hermits, anchorites of the cosmic deep, drifting alone through near-empty space, carrying within themselves memories of an era when the universe was young, when the first galaxies were just forming, when the cosmic dark ages were ending and light was beginning to fill the void. In their faint, steady glow, we glimpse the universe that was, younger, simpler, still learning to create the complexity that would eventually lead to planets, life, and consciousness. They are stellar elders, having witnessed cosmic history unfold over timescales that dwarf human comprehension, silent observers to the birth and evolution of the galaxy itself. When we detect their light, photons that left their surfaces years ago, traveling through space to eventually strike our telescopes, we receive messages from the deep past. Not messages in the usual sense, but information encoded in wavelengths, in spectral lines, in the characteristic signatures of elements present and absent. These ancient stars speak to us across billions of years, their light carrying information about the universe's infancy, waiting patiently for observers capable of understanding the stories written in their spectra. Differential spin. The galaxy's inner rush. In the inner regions of the Milky Way, where stars orbit the galactic center much more rapidly than those farther out, the gravitational pull is stronger. Mass is concentrated. Millions of stars packed into relatively small volumes. the supermassive black hole Sagittarius A contributing its enormous mass. Dense clouds of gas and dust adding to the gravitational potential. This concentration creates fast orbits. Stars near the galactic center can complete a full revolution in just a few million years. Breathtakingly fast by galactic standards. The very innermost stars, orbiting within a few light years of Sagittarius A, complete their circuits in mere decades, their velocities reaching several percent of light speed as they whip around the black hole in elongated ellipses. Moving outward, orbital periods lengthen. In the solar neighborhood, about 26,000 light-years from the center, stars take roughly 225 million years to complete one circuit. In the outer galaxy, orbits stretch to hundreds of millions or even billions of years, stars drifting in the weak gravitational field of the galaxy's outskirts. This differential rotation, the fact that different regions rotate at different speeds, creates shearing motions throughout the disk. Material at different radii moves past other material at different velocities, creating the conditions for density waves to propagate, for spiral arms to form and persist as patterns. The inner galaxy spins like a great wheel, but one whose rim lags behind its hub. If the galaxy rotated as a solid body, with all parts completing orbits in the same time, its structure would be entirely different. Spiral arms couldn't exist in their current form. Density waves couldn't propagate as they do. The whole dynamics of galactic evolution would change. This differential rotation also means that over billions of years, stars wind around the galaxy multiple times, some completing many more orbits than others depending on their starting positions. The galaxy mixes itself through this differential motion, stirring stellar populations, though never mixing them completely. Stars retain memory of their origins through their chemical compositions and orbital characteristics, even as they migrate through the disk. Near the core, the pace of life. If we can speak of galactic life, accelerates, stars orbit faster, encounters are more frequent, supernova rates are higher, the black hole's influence shapes everything. Time itself seems compressed in these inner regions, with stellar generations cycling more rapidly, with dynamical processes operating on shorter timescales. Out in the suburbs where we live, the pace is gentler, more sedate. Our solar system has circled the galaxy perhaps 20 times since its formation. A decent number of circuits, but modest compared to inner region stars that might complete hundreds of orbits in similar timeframes. This creates a kind of temporal layering in the galaxy. Different regions operating at different paces, like a cosmic organism, with fast beating hearts in its center and slower circulation in its extremities. The galaxy is not one clock, but many, each ticking at rates determined by local gravitational conditions, all synchronized by the overall gravitational potential, but each maintaining its own rhythm. Density waves, the pattern that persists. The spiral arms ripple through the galactic disk like waves moving through water, compressing material as they pass, triggering star formation in their wake. These density waves are not made of particular stars remaining fixed in formation, but are patterns, regions of slightly higher density that propagate through the disk. Imagine watching waves roll across an ocean. The wave moves, but the water mostly moves up and down, not horizontally. A particular water molecule rises as the wave passes, then falls back as the wave continues on. The wave is real. It carries energy. It has a definite speed and structure. But it's made of constantly changing water molecules, not a fixed set that travels with it. Similarly, spiral arms are density patterns that rotate through the disk at a particular speed, the pattern speed. While individual stars and gas clouds move at different velocities, drifting into and out of the arms as they orbit. The pattern persists, even though its constituent parts constantly change. As gas clouds enter a density wave, they experience increased gravitational force from the temporarily higher density. This compresses them, raising their internal density and temperature. For clouds already close to gravitational instability, this compression can trigger collapse, initiating star formation, the most massive stars born in these clouds. blue giants and supergiants, live only a few million years. They shine brilliantly, outlining the spiral arms with blue light, but they don't live long enough to drift far from where they formed. Their entire lives, from birth to supernova death, play out within or near the spiral arm that triggered their formation. This is why spiral arms appear bright and blue in galaxy images. They're traced by these short-lived massive stars that form within them and die before leaving them. The arms aren't inherently brighter in terms of total stellar mass, but they contain disproportionate numbers of the brightest, most luminous young stars. Older, longer-lived stars like the Sun pass through spiral arms multiple times during their lives. Each passage might last 10 to 20 million years. Brief compared to stellar lifespans, but long enough for interesting things to happen. Some researchers have speculated that spiral arm passages might influence conditions on Earth, perhaps through increased cosmic ray exposure, though this remains contentious. From a distance, the spiral pattern looks static, permanent, a fixed structure defining the galaxy's appearance. From within, it's a moving pattern, a ripple passing through the stellar disk, inducing responses in the material it encounters, but never composed of the same material for long. This understanding transforms perception. The galaxy isn't a fixed architecture of stable components, but a dynamic system where patterns emerge from collective behavior, where structures persist despite constant replacement of their constituents, where what appears solid and permanent is actually fluid and ever-changing. The arms are not places, but processes, not objects, but patterns held in being by the continuous flow of material through them. They exist like traffic jams exist, as real phenomena with measurable properties, but fundamentally different in nature from the individual vehicles that temporarily compose them. We drift through these patterns, our solar system currently between major arms, having passed through them multiple times in the past, and destined to pass through them again in the future. The spiral structure is not a fixed background against which we move, but a dynamic environment that ebbs and flows, waxes and wanes, shapes and reshapes itself constantly. Star formation, ignition in the darkness. In the coldest, darkest corners of the galaxy, star formation begins not with fire, but with silence. Massive clouds of molecular hydrogen drift through space, chilled to just a few degrees above absolute zero. Temperatures so cold that atoms move in slow motion, their thermal energy almost completely drained away. These molecular clouds can span hundreds of light years, containing enough material to form thousands or millions of stars. They float invisibly through the galaxy, their presence revealed only by their effect on background starlight, which they dim and redden, or by their emission of faint radio waves from trace molecules spinning within the cold gas. Within these clouds, gravity begins its patient work, slight density enhancements, perhaps seeded by passing shock waves, by turbulent eddies in the gas, by the gravitational wake of a spiral arm passage, begin to attract more material. As gas flows inward, density increases. As density increases, gravitational pull strengthens. A feedback loop begins, slow at first, but gradually accelerating. The collapsing region heats as gravitational potential energy converts to thermal energy, but for a long time this heat is radiated away. The cloud remains cold, allowing collapse to continue. Over hundreds of thousands of years, a denser core forms, material accumulating in the center, while the outer regions continue falling inward. Conservation of angular momentum. The tendency of spinning systems to spin faster as they contract causes the collapsing cloud to flatten into a disk. Material can't fall straight inward, but instead spirals down through this disk toward the growing protostar at the center. Eventually, the core becomes dense and hot enough that it becomes opaque. Photons can no longer escape easily, and the interior temperature begins to rise dramatically. Pressure builds, partially supporting the core against further collapse. For a time, the protostar is in balance, not yet a true star, but no longer simply collapsing gas. Finally, when the core temperature reaches about 10 million degrees Kelvin, hydrogen fusion ignites. Protons overcome their mutual electromagnetic repulsion and fuse together, creating helium and releasing tremendous energy. This energy floods outward through the star, creating the radiation pressure that will balance gravity for the star's entire main sequence lifetime. A new star is born from the coldest shadows, from silent compression over immense timescales, from the patient operation of gravity working on cold molecular gas. The process takes perhaps 1 million years from initial collapse to ignition, an eye blink in cosmic time, but an eternity by human standards. The newborn star clears its surroundings through stellar winds and radiation pressure, blowing away remaining gas and dust, revealing itself to the galaxy. If it's massive, it will shine brilliantly but briefly, living just a few million years before exploding. If it's small, like red dwarfs that make up most stars, it might live for trillions of years, potentially outlasting the galaxy itself. From the coldest beginnings come the brightest lights, spun gently into being by gravity's inexorable pull. Each star a small victory of self-organization in a universe that tends toward entropy and disorder. Dissolving clusters, families scattered. Many stars are born not alone but in groups. Stellar clusters formed from the same collapsing molecular cloud, siblings in a gravitational sense, sharing a common origin. These clusters, bound by mutual gravity, drift through the galaxy together, sometimes for millions or even billions of years. Open clusters. Loose associations of hundreds to thousands of stars populate the galactic disk. Young clusters contain bright blue stars, still burning through their initial hydrogen fuel. Older clusters have lost their most massive members to supernova explosions and appear redder, dominated by longer-lived stars. But over time, these clusters dissolve. Tidal forces from the Milky Way's gravitational field work to pull them apart, stronger on the near side than the far side, stretching the cluster along its orbit. Close encounters with massive molecular clouds can disrupt clusters gravitationally, scattering stars. Internal dynamics. The complex gravitational interactions between stars within the cluster cause some members to gain energy and escape, while others become more tightly bound. Stars peel away one by one, gradually enough that the cluster fades rather than suddenly explodes. First, the outermost members drift free, their weak gravitational binding easily overcome. Then, progressively more tightly bound members escape as encounters and tidal forces erode the structure. Eventually, after hundreds of millions or billions of years, little remains. The cluster disperses into the general stellar field of the galaxy, its stars scattered, their common origin evident only through careful analysis of their ages, compositions, and orbital characteristics. Our Sun was likely born in such a cluster, formed alongside hundreds or thousands of siblings about 4.6 billion years ago. That birth cluster has long since dissolved, its members scattered across thousands of light years, most now impossible to identify with certainty among the billions of similar stars in the galactic disk. A few candidates have been proposed. Stars that share the Sun's age and chemical composition, whose orbits suggest they might have originated nearby. But confirming sibling relationships is difficult. The galaxy has had 4.6 billion years to scramble stellar positions, mixing and scattering until recovering family connections becomes extraordinarily challenging. Imagine this. Somewhere in the night sky, perhaps visible from your location, perhaps on the other side of the galaxy, the Sun's birth siblings still shine. They formed from the same molecular cloud, condensed from the same enriched gas, perhaps even influenced one another gravitationally during their first few million years before the cluster dispersed. They are family in the truest sense, made of the same material, born in the same cradle, sharing the same origin story, even though they've been separated for billions of years and will never reunite. The galaxy has scattered them like seeds, each following its own path through the cosmic night, all carrying within themselves a common heritage they no longer recognize. This scattering is inevitable, written into the dynamics of open clusters from their birth. They are temporary structures, bound together for a time, but destined to dissolve, their stars becoming part of the general galactic population. In this way, the galaxy continuously mixes itself, breaking up concentrations, spreading stellar populations, ensuring that stars of many ages and origins occupy any given region. We are part of this scattered family, our Sun one orphaned member among many, all drifting through the galaxy on independent paths, all carrying within themselves fragments of a shared past that existed before planets, before life, in an era when our solar system was just one collapsing core among many in a bright stellar nursery that no longer exists, except as its dispersed children, shining separately across the galactic night. The most metal poor, echoes of first light. Among the rarest and most precious objects in the Milky Way are the hypermetal poor stars, ancient suns whose atmospheres contain almost no elements heavier than helium. Some contain less than 1/10,000th the iron found in our own sun. They are so chemically pure they seem almost impossible, relics from an era when the universe barely knew how to make anything beyond hydrogen and helium. These stars are believed to be among the first generation born after the very first supernovae, those primordial explosions that seeded the cosmos with its initial traces of heavy elements. They formed from gas clouds that had been touched only slightly by stellar death, enriched just enough to allow star formation, but still overwhelmingly primordial in composition. Finding them requires patience and dedication. They hide among billions of younger, brighter stars, their faint red glows easily overlooked. But when astronomers locate one, it becomes a treasure. A physical sample of conditions that existed over 13 billion years ago, a living connection to the universe's chemical infancy. Each hypermetal poor star is a kind of relic, a gravitationally bound signature from a near-forgotten epoch. Their spectral lines tell stories of a simpler cosmos, before stellar generations had time to build up the periodic table, before the universe had learned to create the chemical complexity that would eventually enable rocky planets, organic chemistry, and life itself. In their atmospheres, astronomers find clues about the very first stars. The population 3 stars that have never been directly observed because they all died billions of years ago. The pattern of elements present in hypermetal poor stars reflects the nucleosynthesis yields of those first stellar explosions, allowing scientists to constrain theories about what those primordial giants were like. Some hypermetal poor stars show unusual abundance patterns, excess carbon, peculiar ratios of oxygen to iron, unexpected amounts of certain rare elements. These oddities suggest they were enriched by specific types of supernovae, perhaps from stars, with unusual properties possible only in the metal-free environment of the early universe. They are fossils made not of stone, but of light and plasma, their chemical compositions preserving information about cosmic conditions that existed before most of what we see had taken form. They drift through the halo, ancient and patient, their faint light carrying messages from the universe's dawn, waiting across billions of years for observers capable of understanding the profound stories written in their spectral signatures. When we study these stars, we're engaging in a form of temporal archaeology, examining physical remnants from the deep past, reading chemical records that stretch back almost to the beginning of cosmic time. Each element detected or absent tells part of the story. Each ratio measured constrains what happened in those first stellar furnaces. Close your eyes and imagine that faint red star drifting through the galactic halo might have witnessed the formation of the Milky Way itself. It might have been born when the galaxy was still assembling from smaller fragments, still learning its shape, still violent with mergers and collisions. It has survived everything. Billions of years of cosmic evolution, galaxy after galaxy collision, supernova after supernova, while maintaining its tiny nuclear furnace, slowly converting hydrogen to helium, glowing quietly in the dark. These ancient survivors connect us to a time we can barely imagine. A universe younger and simpler, before complexity had time to emerge, before the slow alchemy of stellar nucleosynthesis had created the elements necessary for worlds like Earth. They remind us that everything has a history, that the current state of the cosmos is just one moment in a much longer story, and that if we look carefully enough, we can find witnesses to epochs long past, their testimony preserved in the atoms that compose them. Planetary systems, worlds beyond counting. Planets are not rare accidents, but natural consequences of star formation. As a new star ignites at the center of a rotating disk of gas and dust, the leftover material doesn't simply disappear. It continues orbiting, and within this protoplanetary disk, particles stick together. First microscopic grains clumping into pebbles, then pebbles accumulating into boulders, boulders into planetesimals, planetesimals into planetary embryos, and finally embryos into full-fledged worlds. This process unfolds over millions of years, hidden behind veils of dust, detectable only through infrared observations that can penetrate the obscuring material. Gradually, a solar system emerges. Rocky planets close to the star where temperatures are high, giant planets farther out where volatile compounds like water and methane can condense, icy bodies in the outer reaches where the sun's warmth barely reaches. Across the Milky Way, this process repeats billions of times. Planetary systems are not exceptions but rules, natural products of the star formation process. Recent observations suggest most stars harbor planets, perhaps averaging more than one planet per star across the galaxy. This means the Milky Way contains hundreds of billions of planets, perhaps more. Rocky worlds like Earth, gas giants like Jupiter, ice giants like Neptune, super-Earths with no solar system analog, hot Jupiters orbiting impossibly close to their stars, rogue planets drifting between stars with no sun to warm them. The diversity is staggering. Some systems resemble our own, with small rocky planets in the inner system and giants farther out. Others defy our expectations entirely. Massive planets in tight orbits, planetary systems around binary stars, worlds orbiting the remnants of dead stars. Each system is unique, shaped by the particular conditions in its forming disk, by gravitational interactions that scattered some planets and stabilized others, by the specific amount and composition of material available. The galaxy is not just full of stars, it is full of systems, of solar families, each with its own unique balance, orbit, and potential. Every point of light in the night sky might be surrounded by worlds, some barren and lifeless, others perhaps teeming with biology we cannot yet imagine. This realization transforms how we see the universe. We exist not in a galaxy of isolated stars, but in a galaxy of planetary systems, a cosmos populated with uncountable worlds, each one a distinct environment with its own characteristics, its own story, its own possibility. Some of those worlds might be havens for life, planets orbiting in habitable zones where temperatures allow liquid water, where atmospheres protect surfaces from harmful radiation, where conditions remain stable over billions of years. Others might host life in forms we wouldn't recognize, adapted to environments we consider hostile. Worlds orbiting red dwarfs bathed in infrared light, moons around gas giants heated by tidal forces, subsurface oceans beneath thick ice shells. The question is no longer whether other worlds exist. We know they do, in overwhelming abundance. The question is whether life has arisen elsewhere, whether consciousness has emerged in other locations, whether we are alone in our awareness or part of a much larger community of minds scattered across the galactic disk. We cannot yet answer these questions definitively, but we exist in a galaxy rich with possibilities, a cosmos that creates worlds as readily as it creates stars, a universe that seems almost profligate in its production of places where complexity might arise. Breathe deeply and consider. Orbiting distant suns, perhaps visible in tonight's sky, worlds turn. Some may be dead, sterile rocks or frozen ice balls, but others might be alive in ways we're only beginning to imagine. And if even one of those worlds has developed consciousness, has looked up at its own night sky, and wondered about the lights it sees there, then we are not alone. We are part of something larger, a cosmic community separated by vast distances, but united by the miracle of awareness. The co-rotation radius, a resonant home. In the Milky Way's complex dynamics, there exists a special distance from the galactic center called the co-rotation radius, a location where the average orbital velocity of stars matches the rotation speed of the spiral arm pattern. Here, stars drift through spiral arms at nearly the same rate the arms themselves rotate, spending extended time within the density waves. Earth's sun orbits close to this boundary, perhaps just inside the co-rotation radius. This positioning may be more than coincidence. It might represent a form of cosmic good fortune that has protected the solar system from some of the hazards associated with frequent spiral arm passages. Outside the co-rotation radius, stars orbit faster than the spiral pattern, regularly overtaking the arms and passing through them. Each passage takes them through regions of higher stellar density, increased supernova rates, enhanced cosmic ray flux, and stronger gravitational perturbations. These crossings might represent periodic environmental challenges for any life existing in those systems, not necessarily fatal, but potentially disruptive. Inside the co-rotation radius, but far from it, stars orbit slower than the pattern, allowing spiral arms to overtake them from behind. Again, frequent crossings result in periodic environmental variations. But near the co-rotation radius, the gentle match in motion minimizes crossing frequency. Stars spend longer times between spiral arms or move through them more gradually, experiencing less dramatic environmental change. This resonant location might represent a more stable galactic neighborhood, shielded not by physical barriers, but by dynamical resonance, by a coincidental matching of velocities that keeps the solar system in relatively calm galactic waters. We live, quite possibly, in one of the galaxy's more stable zones, not by design, but by the accident of where our molecular cloud happened to form, what orbital parameters our solar system inherited, how the complex choreography of galactic rotation positioned us near this special radius. This is yet another layer in the nested series of cosmic coincidences that enable our existence. The right planet, orbiting the right star, located in the right part of the galaxy, at the right distance where orbital motion and spiral pattern rotation approximately match. Each requirement narrows the possibilities, but together they create the stable environment that allowed life billions of years to evolve from single cells to consciousness. Whether this represents genuine cosmic fortune or observational selection bias, the anthropic principle suggesting we necessarily find ourselves in locations where life can exist remains philosophically debatable. But either way, we exist here, in this resonant region, protected by invisible dynamics from some of the galaxy's harsher environments. The sun doesn't glide motionless through space, but follows a complex path, a bobbing, weaving trajectory that oscillates above and below the galactic plane while simultaneously circling the galactic center. This vertical oscillation, with a period of about 60–70 million years, causes the solar system to rise and fall through the disk like a cork gently bobbing in slow motion. Some researchers have speculated whether this oscillation might correlate with patterns in Earth's geological or biological history. Periodic increases in comet impacts when passing through the densest part of the disk, possible correlations with mass extinctions, climate variations influenced by changing cosmic ray exposure. The evidence remains inconclusive and controversial, but the possibility illustrates how even on its apparently steady path around the galaxy, the sun is not simply gliding, it's swaying, oscillating, following a complex three-dimensional trajectory through space. We exist in a dynamic environment, embedded in motion at every scale. The Earth rotates daily, the Moon circles monthly, the Earth orbits yearly. The solar system oscillates vertically over tens of millions of years, while simultaneously orbiting the galactic center over hundreds of millions of years. The Milky Way moves through the local group. The local group falls toward the Virgo cluster. At every level, motion is fundamental, stillness an illusion born of limited perspective and brief observation. Dark matter's domain. Dark matter makes up most of the Milky Way's mass, yet it has never been seen directly, never been touched, never been isolated in a laboratory. It does not emit light, does not absorb radiation, does not interact electromagnetically with ordinary matter. It passes through us constantly, through the Earth, through the Sun, as if we weren't there. Billions of dark matter particles streaming through your body every second, depositing no energy, leaving no trace, and yet we know it exists with extraordinary confidence, because its gravitational effects are unmistakable. It holds the galaxy together against the centrifugal forces that should tear it apart. It explains the unexpected rotation speeds of stars in the outer galaxy. It shapes the large-scale structure of the universe, creating the cosmic web of filaments and voids that galaxies trace. It leaves subtle imprints in the cosmic microwave background, in the distribution of galaxies, in the dynamics of galaxy clusters. Without dark matter, galaxies would fly apart, their visible mass insufficient to gravitationally bind their rapidly orbiting stars. Without dark matter, the universe would look completely different. Galaxy clusters couldn't form, the cosmic web wouldn't exist, structure on the largest scales couldn't arise. Dark matter is not a minor correction to our models, but fundamental to cosmic architecture. Astronomers detect it not by seeing it, but by watching how it moves other things. Stars orbiting faster than they should, galaxies lensing background light more strongly than their visible mass explains, clusters containing far more gravitational mass than their stars and gas can account for. The Milky Way swims in a sea of dark matter, a vast halo extending perhaps 600,000 light-years from the galactic center, far beyond the visible disk's edge. This halo is not uniform, but structured, containing streams from disrupted satellite galaxies, clumps and subhalos, predicted by simulations. Complex three-dimensional architecture, invisible to all our instruments, except through its gravitational influence. Most of the galaxy's mass resides in this invisible component. When we look at the Milky Way, we see only the luminous surface, the stars and gas and dust that happens to shine or obscure light. But this visible matter represents perhaps 15–20% of the total mass. The rest is dark matter, invisible scaffolding that determines the galaxy's gravitational potential, its rotation curve, its ability to hold itself together against the violence of its own motion. We don't know what dark matter is made of. This ignorance should humble us profoundly. We have identified that most of the universe's mass exists in a form we don't understand, governed by physics we haven't discovered, interacting through mechanisms we can only infer indirectly. Candidates abound: WIMPs, axions, sterile neutrinos, primordial black holes, modifications to gravity itself. Decades of experiments have searched for direct detection, trying to catch the incredibly rare interactions that might occur when dark matter particles pass through sensitive detectors. So far, despite extraordinary experimental sophistication, dark matter remains undetected through any means except gravity. This should inspire both humility and wonder. Humility because we live in a universe made primarily of something we don't understand, our knowledge incomplete in the most fundamental way. Wonder because this mystery represents an entire realm of physics waiting to be discovered, particles and forces and interactions beyond our current theories, a deeper level of reality hiding behind the visible cosmos. Every second, as you rest here, trillions of dark matter particles pass through you. They interact so weakly that they traverse your body, the Earth, the entire Sun, without leaving any evidence of their passage. They are ghosts in the cosmic machine, invisible, yet essential, the hidden majority that makes everything else possible. The universe is not what it appears. Most of reality is invisible, detectable only through its gravitational influence, fundamentally mysterious despite being fundamental to existence. We inhabit a cosmos where the seen is the minority and the unseen dominates, where the visible universe floats like foam on an invisible ocean, where most of what exists remains hidden from all our senses and nearly all our instruments. And yet we persist in trying to understand. We build ever more sensitive detectors, develop ever more sophisticated theories, search with growing determination for direct evidence of this elusive substance. Because humanity cannot rest with mystery. We must probe, question, seek answers, even when those answers lie hidden in forms of matter that barely touch our own. Dark matter is the galaxy's secret keeper, the invisible foundation on which everything visible rests, the hidden truth that makes the cosmic story possible. Mass beyond the visible edge. Most of the Milky Way's visible stars lie within the luminous disk, that flat spiral structure extending perhaps 50,000, 60,000 light-years from the center. But the majority of the galaxy's mass resides elsewhere, in the dark matter halo extending far beyond the furthest stars. This halo is enormous, dwarfing the visible structure. It may extend 600,000 light-years or more from the galactic center, encompassing a volume hundreds of times larger than the disk. Within this vast region, dark matter dominates overwhelmingly, outweighing visible matter by factors of 5 or 10 to 1. Scattered through this halo are ancient stars and globular clusters, but they're sparse. The halo's stellar density is thousands of times lower than the disk's. Most of the halo is nearly empty of visible matter, populated primarily by invisible dark matter, whose presence we infer only through gravitational effects. This invisible halo holds the galaxy together. Its gravitational potential determines how fast stars can orbit without escaping. Its mass shapes the overall rotation curve. Its structure influences how satellite galaxies interact with the Milky Way, determining which will be absorbed and which might survive as independent systems. When we picture the Milky Way, we naturally envision its visible components: the bright disk, the central bulge, the spiral arms glowing with young stars. But that's only the glowing surface, the luminous tip of a much larger structure. The true Milky Way extends vastly farther, mostly invisible, mostly dark, mostly mysterious. This invisible majority is not evenly distributed, but structured. Simulations predict it contains streams from disrupted dwarf galaxies, subhalos that were once independent objects before being captured. Complex three-dimensional architecture shaped by billions of years of hierarchical merging, the mass that defines the galaxy. Its gravity, its motion, its reach into space is mostly hidden, enveloping everything like a quiet shroud. We live in the bright center of a much larger darkness, inhabitants of a luminous island floating in an invisible ocean that extends far beyond what eyes or telescopes can see. This should recalibrate our sense of scale. The galaxy we perceive is a small part of the galaxy that exists. The structure we study through starlight is embedded in a much larger structure detectable only through gravity. We are not seeing the galaxy whole, but only its brightest parts, the regions where ordinary matter has gathered and begun to shine. The rest, the vast majority, remains hidden, not because it's far away or obscured by dust, but because it simply doesn't interact with light. It is there, shaping everything, determining the galaxy's fate, but forever invisible to direct observation. We exist in a cosmos where most of reality cannot be seen, where the fundamental nature of most mass remains unknown, where our understanding is necessarily incomplete. And yet we continue trying to understand, building theories from incomplete data, inferring the invisible from its influence on the visible, slowly mapping an unseen universe through its gravitational shadow. The quasar that was. Today the heart of our galaxy appears relatively quiet. Sagittarius A sleeps, consuming only modest amounts of material, producing little radiation compared to its enormous mass. But evidence suggests this has not always been so. The galaxy's core may once have been dramatically more active, blazing like a quasar, one of the brightest objects in the universe. Quasars are active galactic nuclei where supermassive black holes consume enormous amounts of matter, heating it to millions of degrees as it spirals inward. The resulting radiation can outshine an entire galaxy, visible across billions of light-years of space. If the Milky Way once burned like this, it would have looked completely different. A spiral wrapped around a blinding beacon of light. The Fermi bubbles provide evidence for this past activity. These enormous gamma-ray structures extending above and below the galactic center suggest a massive energy release within the last few million years. possibly from intense accretion onto Sagittarius A, possibly from a burst of star formation, or perhaps both processes working together to drive tremendous amounts of energy out of the galactic core. Other evidence comes from light echoes, radiation reflected off gas clouds thousands of light years from the center, carrying the signature of far more intense radiation in the past. These clouds glow faintly with X-rays, illuminated not by current conditions but by light that left the core thousands of years ago when it was far more active. If the Milky Way experienced a quasar phase, it would have been a different kind of galaxy, its core blazing with radiation that sterilized nearby regions, its central black hole growing rapidly, its inner structure shaped by powerful winds and jets ejecting material perpendicular to the disk. That time has passed. The black hole has consumed most of the easily accessible material in its vicinity. The remaining gas orbits at distances where it falls inward only slowly. The galaxy has entered a quieter phase, its core sleeping, its most violent era perhaps behind it. But this sleep might not be permanent. If a new source of fuel arrived, perhaps gas clouds falling inward, perhaps a dwarf galaxy delivering fresh material to the central regions, Sagittarius A could wake, blazing again with the light of vigorous accretion. The galaxy's history might not be finished, merely paused between more active episodes. These cycles of activity and quiescence may be common in galactic evolution. Many galaxies show evidence of past activity far exceeding their current state. Black holes grow through episodic feeding, gorging when material is available, sleeping when they've cleared their surroundings, waiting perhaps billions of years between major feeding events. The Milky Way's current peaceful appearance may be temporary, a lull between storms, a quiet moment in a longer story that includes periods of dramatic change. The echoes of past violence remain, in the Fermi bubbles, in light echoes, in the structure of the central regions shaped by ancient outbursts. Reminders that the galaxy has been capable of far more dramatic behavior than what we currently observe. Ever-changing structure. Galaxies may appear timeless in images, unchanging spirals frozen in space, but they are always evolving. Spiral arms shift position over hundreds of millions of years. Bars form, strengthen, and potentially dissolve over billions of years. Gas flows inward and outward, redistributing material. Stars are born and die, changing the population characteristics. Dark matter, halos grow and restructure through ongoing accretion. Even the shape of the Milky Way's disk, warped, rippling, lopsided, changes slowly over time. Encounters with dwarf galaxies create disturbances that take hundreds of millions of years to settle. Streams from disrupted satellites gradually disperse and fade. The thick disk may still be adjusting to ancient merger events, its structure not yet fully relaxed. Over billions of years, the galaxy's silhouette shifts like a drifting cloud. The Milky Way of 4 billion years ago, when Earth was forming, looked similar to today's galaxy, but with differences in spiral arm configuration, stellar populations, gas content. The Milky Way of 4 billion years hence, when the Sun enters its red giant phase, will look different again, perhaps beginning to show signs of interaction with the approaching Andromeda galaxy, perhaps having accreted additional dwarf galaxies, perhaps showing different spiral structure. The galaxy is not a fixed monument but a dynamic entity, always changing, always responding to internal and external forces, always evolving toward whatever configuration the interplay of gravity, gas dynamics, and stellar evolution produces. This impermanence might seem melancholy. Nothing lasts, even galaxies transform beyond recognition given enough time. But there's beauty in it too, a reminder that the universe is alive with process and change, that the cosmos is not static but constantly becoming something new, that transformation is written into the fundamental nature of reality at every scale. The Milky Way of today is not the one that was, and not the one that will be. Its current beauty lies not in permanence, but in being a particular moment in a much longer evolution, a snapshot of one configuration in an ongoing story of growth, collision, transformation, and renewal. Gravitational waves. ripples through space-time. All across the universe, massive objects spiral together in gravitational dances that end in cataclysmic mergers. Black holes circle each other in decaying orbits, gradually drawing closer until they finally collide. Neutron stars, the collapsed cores of dead massive stars, pair up and spiral inward. Entire galaxies merge, their central black holes eventually meeting in the merged core. These events send out gravitational waves, literal ripples in the fabric of space-time itself, traveling outward at light speed, stretching and squeezing space as they pass. Though predicted by Einstein's general relativity over a century ago, these waves are incredibly difficult to detect because they distort space by only tiny amounts, less than the width of an atomic nucleus, even for powerful sources. Some of these waves pass through the Milky Way, having traveled perhaps billions of light years from distant mergers. They're incredibly faint by the time they reach us, but observatories like LIGO and Virgo have successfully detected dozens since the first confirmed observation in 2015. Each detection reveals something about its source: the masses of the merging objects, how fast they were spinning, how far away they were when they collided. Together, these observations are creating a new form of astronomy, one that observes the universe not through light, but through gravitational radiation. Even now, as you rest, space itself shifts around you. Not enough to feel, far too subtle for human senses to detect, but measurable with sufficiently sophisticated instruments. Somewhere far away, the universe is changing. Black holes are merging. Neutron stars are colliding. Gravitational potential energy is being converted to gravitational waves that propagate outward, carrying news of these cosmic events to any observers capable of detecting them. This represents yet another layer of cosmic communication. The universe speaks in light, in particles, in neutrinos, in magnetic fields, and now we've learned to hear it speak in gravitational waves as well. Vibrations of space-time itself, a language that required a century of technological development before humanity could begin to understand it. The Milky Way exists bathed in these waves, embedded in a sea of gravitational radiation from sources near and far. Most waves are too weak to detect with current technology, but they're there, constantly passing through, carrying information about the universe's most violent events, connecting us through ripples in space-time to catastrophes occurring billions of light years away, stars on elongated journeys. Not all stars move in neat circles around the galactic center, following the orderly rotation that defines the disk's general motion. Some follow long, stretched ellipses, their paths looping high above and far below the galactic plane, tilted at odd angles from the main structure, carving trajectories through space that speak of disrupted origins and chaotic pasts. These stars drift like messengers from broken systems, their orbits carrying stories written in gravitational memory. Many likely came from dwarf galaxies swallowed by the Milky Way billions of years ago. When a smaller galaxy merges with a larger one, its stars don't simply settle into circular orbits matching the disk's rotation. Instead, they retain echoes of their original motion, velocities that don't match the Milky Way's rotation, inclinations that carry them perpendicular to the plane, eccentricities that send them on long elliptical journeys through the halo. Others might be survivors of ancient gravitational upheavals, stars scattered by close encounters, ejected from clusters by three-body interactions, or flung onto unusual orbits by past merger events that heated the disk and scrambled stellar velocities. Each unusual orbit is a clue, a fossil record of violence or disruption, preserved not in rock or ice, but in the eternal mathematics of trajectory and momentum. By tracing their motion backward and forward, astronomers reconstruct the invisible architecture of the Milky Way's mass distribution. These stars respond to gravity from all sources. Visible stars, molecular clouds, dark matter concentrations. Their orbits reveal where mass resides, both seen and unseen, mapping the galaxy's gravitational landscape through the paths of particles falling through it over billions of years. These wanderers move through the galaxy like memory itself, carrying forward into the present evidence of past events, their trajectories shaped by forces that acted long ago, their paths determined by initial conditions set in epochs now vanished. They are the galaxy's record keepers, their orbits an archive written in motion, readable by those who understand the language of gravity and time. Imagine one such star, born in a dwarf galaxy that no longer exists, orbiting peacefully for billions of years in that smaller system, then watching as the Milky Way's gravity tore everything apart. The parent galaxy dissolved over hundreds of millions of years, its stars scattered into streams, its identity lost. But this star survives, following the orbit it was given by that ancient disruption, looping endlessly through space. Alone now, but still carrying within its trajectory the memory of its origin, still tracing a path determined by a collision that ended epochs ago. The galaxy is full of such travelers, each following its unique path, each carrying its own story, together creating a three-dimensional tapestry of motion that reveals the Milky Way's hidden history and invisible structure. Neutrinos, ghostly messengers. Every second, trillions upon trillions of neutrinos pass through your body, straight from the stars, from the sun, from supernova explosions, from cosmic rays colliding with atoms in space. These ghostly particles are produced in nuclear reactions deep within stellar cores, in the catastrophic collapse of dying massive stars, in the decay of radioactive elements drifting through the cosmos. The Milky Way is bathed in them, an invisible sea of weakly interacting particles that permeate every cubic centimeter of space, streaming outward from every source of nuclear reactions, passing through planets and stars and living things as if matter barely existed. Yet they are so light, so ethereally insubstantial, so unwilling to interact with ordinary matter that they slip through almost everything undetected. A neutrino could pass through a light year of solid lead and have only a small chance of interacting with a single atom. They are the ultimate ghosts, present but intangible, everywhere but unnoticed, carrying information from places we cannot see, but rarely depositing any of that information where we can read it. Detecting them requires extraordinary measures. Special observatories buried deep underground or under Antarctic ice wait patiently for the incredibly rare occasions when a neutrino does interact with an atom, producing a brief flash of light. From these rare signals, scientists reconstruct the properties of neutrinos passing through, their energies, their directions, clues about their sources. Neutrinos carry information from stellar cores, from the innermost hearts of stars where nuclear fusion occurs in darkness and pressure beyond imagination. Light from those cores takes tens of thousands of years to random walk outward through the star's mass before finally escaping from the surface. But neutrinos escape immediately, streaming outward at nearly the speed of light, passing through the entire star as if it weren't there. When a massive star collapses in a supernova, it releases most of its gravitational binding energy as neutrinos, an overwhelming flood of particles carrying away 99% of the explosion's energy. These neutrino bursts can be detected even across galactic distances, arriving hours before the light from the explosion because they escape immediately while light must fight its way through the exploding stellar envelope. They are whispers of cosmic fire, messages from the heart of nuclear furnaces, information carriers from the galaxy's most violent events. They speak of conditions and processes occurring in places we can never directly observe. Stellar interiors, collapsing cores, the centers of active galactic nuclei where matter spirals toward black holes. Even now, neutrinos from the sun pass through you by the billions every second. Particles created in fusion reactions at the sun's core 8 minutes ago, racing outward at light speed, passing through the Earth's bulk without slowing, continuing onward into space beyond. You are transparent to them, hardly existing in their universe of weak interactions and ghostly transit. The galaxy speaks in many voices, and neutrinos represent one of its subtlest, a language we've only recently learned to hear, a whisper beneath the more obvious signals of light and gravity, carrying messages from hidden realms. The turbulent sea of space. Between the stars, space is not smooth or calm, but turbulent, a slow-motion chaos of flows and eddies, shock waves and magnetic tangles, expanding bubbles and colliding streams. The interstellar medium, thin as it is, behaves like a fluid on large scales, and like all fluids, it becomes turbulent. Supernova inject energy violently, creating blast waves that propagate for thousands of years, stirring and heating vast regions. Stellar winds from massive young stars push outward constantly, carving cavities and driving flows. Spiral density waves compress gas as they pass, triggering instabilities. Magnetic fields twist and reconnect, releasing stored energy in sudden bursts. All these processes create a turbulent environment. Not the smooth, empty void we might imagine, but a dynamic, roiling sea where material flows in complex three-dimensional patterns, where shock fronts collide and merge, where temperature and density vary wildly across relatively small distances. This turbulence affects everything. It influences how molecular clouds collapse. Turbulent motions provide support against gravity, slowing collapse and affecting the masses of stars that eventually form. It shapes magnetic field structures, tangling field lines into complex configurations. It determines how cosmic rays propagate, how heavy elements mix through the galaxy, how energy moves from regions of injection to regions where it's radiated away. On large scales, this creates a kind of weather system. Slow-moving patterns of hot and cold gas, expanding bubbles that rise and cool, falling streams that descend and heat, circulation patterns that span thousands of light years and persist for millions of years. What looks from afar like calm starlight is up close a dynamic, rippling fabric shaped by invisible winds and ancient energy. Star formation emerges from this chaos. Dense regions within turbulent clouds become gravitationally unstable and collapse despite the turbulent motions trying to disperse them. The exact balance between turbulent support and gravitational attraction determines whether a cloud fragments into many small stars or collapses into fewer, more massive ones. The interstellar medium is not a passive background, but an active participant in galactic evolution, stirred by stellar feedback, shaped by spiral structure, threaded with magnetic fields, filled with invisible motion at every scale. It is the sea in which stars swim, the medium from which they're born and into which they eventually die, the recycling system that makes galactic evolution possible. Close your eyes and sense it. You exist embedded, not in emptiness, but in this dynamic medium. Earth moves through the local bubble, a region of hot, tenuous gas carved by ancient supernova. The heliosphere, the magnetic bubble blown by the sun's wind, protects the planets from the full force of the interstellar medium's pressure and radiation. We drift through this turbulent sea, sheltered within our stellar cocoon, but still part of the larger flows and structures that make the galaxy a living, breathing entity. Rogue planets, children of darkness. Planets are not always tethered to stars, not always held in gravitational embrace by the warmth and light of a sun. Some drift alone through the galaxy, cold, dark wanderers following their own paths through the cosmic night, orphaned or perhaps never parented, moving through space with no star to call home. These are rogue planets, and they may be astonishingly common. Some formed normally in protoplanetary disks, but were later ejected, hurled out of their birth systems by gravitational interactions with other planets, scattered by close encounters, cast out by orbital instabilities that cleared them from their solar families. Others may never have had a star at all, forming directly from collapse in molecular clouds, mini-worlds born from the same processes that create stars but lacking sufficient mass to ignite fusion. They are difficult to detect. No star illuminates them, no reflected light makes them visible. Only occasionally, through gravitational microlensing events when they pass in front of background stars, do we catch glimpses of their presence, or through infrared observations that might detect their residual heat, the faint warmth left over from formation, slowly radiating into space over billions of years. Studies suggest billions of them may exist in the Milky Way. Perhaps more rogue planets than stars, a hidden population of worlds drifting through the darkness between stellar systems. Some may be rocky like Earth, others gas giants like Jupiter, still others ice worlds, or types we have no names for. Without stars to warm them, these worlds are frozen in eternal night. Their surfaces, if they have surfaces, exist at temperatures barely above absolute zero. Any atmospheres would be frozen solid against the ground. Any oceans that once existed have long since become ice kilometers thick, yet they are not necessarily lifeless. Internal heat, from radioactive decay, from tidal heating if they have large moons, from leftover warmth of formation, might maintain subsurface oceans beneath thick ice shells. Life, if it arose in those hidden seas during the planet's youth when it still orbited a star, might persist even after ejection, sustained by heat from below and chemical energy from hydrothermal systems. Some may wander through the galactic halo, flung so far from their origins that they move through nearly empty space, encountering another star only once in trillions of years. Others might remain in the disk, part of the general stellar population, but invisible. Dark points moving through the darkness, their presence revealed only by rare gravitational encounters. They are the galaxy's orphans, planetary drifters following long, lonely paths through space. If they harbor life, those biospheres exist in absolute isolation, cut off from stellar light, dependent entirely on internal energy sources, perhaps never aware that beyond their frozen shells lies a galaxy full of stars and light. Imagine such a world, once warmed by a sun, perhaps once home to surface oceans and skies, then cast out by orbital chaos, its star growing distant and dim, finally winking out altogether as the planet drifted beyond rescue. Over millions of years, the surface froze. Atmospheres collapsed. Any life that survived retreated deeper, into cracks and caverns, into subsurface oceans, adapting to eternal darkness. And now it drifts, alone in the dark, perhaps for billions of years, perhaps forever. A world without a sun, a planet without a home, moving through the galaxy like a ghost, invisible and forgotten, its story known only to itself. Magnetic choreography, the dance of dust, interstellar dust, those microscopic grains of carbon and silicate, each smaller than cigarette smoke particles, moves not just under gravity's influence, but also under the subtle push and pull of magnetic fields threading through the galaxy. These fields, though weak, guide charged particles and influence dust grains that carry slight electric charges or contain magnetic materials. In some regions, dust grains spin rapidly, their rotation driven by collisions with photons and gas atoms, creating faint microwave emission detectable by sensitive instruments. In others, they align with magnetic field lines, their long axes pointing preferentially along field directions, causing the starlight passing through them to become polarized. A subtle effect that reveals the hidden magnetic architecture. Understanding these effects helps astronomers trace magnetic field structures throughout the galaxy. Dust becomes a tracer, its alignment and behavior revealing invisible forces, its polarization signature mapping currents of magnetism flowing through space. This information is crucial for understanding not just magnetic fields themselves, but also how they influence star formation, cosmic ray propagation, and galactic dynamics. Dust is not passive but responsive, dancing to magnetic rhythms, falling into patterns determined by invisible forces. It aligns, rotates, clusters in ways shaped by electromagnetic interactions, creating a choreography that plays out across light years, determined by field configurations that themselves are shaped by galactic rotation, stellar winds, supernova shocks, and turbulent motions in the interstellar medium. These magnetic rivers flow through the galaxy unseen, their currents revealed only through careful observation of how dust and gas respond to their influence. They connect regions separated by vast distances, creating pathways along which cosmic rays travel, channels through which energy flows, structures that shape how the galaxy evolves. Breathe slowly and imagine these invisible currents surrounding you. Magnetic field lines threading through space, dust grains aligning in response, charged particles spiraling along field directions, energy flowing through channels defined by electromagnetism rather than gravity. The galaxy is not held together by gravity alone, but also by these subtler forces, these electromagnetic connections that link distant regions and shape the medium through which everything moves. We exist embedded in these fields, though we rarely sense them. Earth's magnetic field shields us from solar wind, but that field is itself a tiny eddy in the larger galactic magnetic structure. We drift through cosmic magnetic rivers without feeling them, protected by our planet's magnetosphere, largely unaware of the electromagnetic architecture that surrounds us on all scales. The universe speaks not just in gravity and light, but in magnetism, a quieter language, a subtler force, but one fundamental to cosmic structure and evolution. To understand the galaxy fully, we must learn to read these invisible signatures, to trace the magnetic threads that weave through space, connecting, shaping, guiding the matter from which everything arises. Neutron star alchemy, forging the heaviest elements. When two neutron stars spiral together and collide, they create one of the universe's most violent events. A kilonova, an explosion that briefly outshines millions of suns and forges tremendous quantities of heavy elements in a single cataclysmic moment. Neutron stars are the collapsed cores of massive stars, each containing about 1.4 solar masses, compressed into a sphere perhaps 20 kilometers across. So dense that a teaspoon of neutron star material would weigh billions of tons. When two orbit each other closely, they gradually lose energy through gravitational wave emission, their orbits decaying over millions or billions of years, until finally they merge. The collision releases enormous energy. For a few seconds, the event creates conditions even more extreme than supernova. Temperatures reaching trillions of degrees, densities exceeding nuclear matter, neutron-rich environments where rapid neutron capture can build up the heaviest elements in the periodic table. Gold, platinum, uranium, thorium, rare earth elements. These and many other heavy elements are forged primarily in neutron star mergers, created through rapid neutron capture processes that can only occur in such extreme environments. The explosion scatters these newly forged elements into space, mixing them with the interstellar medium, making them available for incorporation into later generations of stars and planets. Some stars in the Milky Way carry the chemical fingerprints of these rare events, their spectra showing unusual enrichment in elements that could only have come from neutron star collisions. They are not just luminous bodies, but record keepers of ancient cataclysms, burning with the residue of stellar mergers that occurred billions of years ago, their atmospheres containing atoms forged in the most violent seconds the universe can produce. Every gold atom in existence was likely created in a neutron star merger or similar catastrophic event, forged in temperatures and densities that briefly approached those existing microseconds after the Big Bang itself, then scattered into space to drift for billions of years before perhaps being gathered into planets, mined by civilizations, crafted into jewelry or electronics or art. The gold ring on someone's finger, the platinum in catalytic converters, the uranium in nuclear reactors. All came from these cosmic catastrophes, from moments when two dead stars crashed together and briefly became alchemical furnaces, transmuting lighter elements into heavier ones through processes so extreme they can only occur when stellar remnants collide. We are surrounded by evidence of ancient violence, the heavy elements in our bodies, our technology, our world. All were created in events of unimaginable energy, scattered through space, gathered by gravity into new structures, eventually becoming part of the stable, peaceful world we inhabit. The universe builds complexity through catastrophe, creates through destruction, forges the elements necessary for life and civilization in its most violent moments. Beauty and violence are intertwined at cosmic scales, creation and destruction inseparable. The universe's productive capacity linked inextricably to its capacity for extreme events, the galaxy within and without. And now, dear traveler, we return, not to Earth precisely, but to a deeper understanding of what Earth is, where it exists, what it means to be here, now, in this particular arrangement of atoms on this particular world, orbiting this particular star, in this particular galaxy. You have drifted through stellar nurseries where suns are born from cold darkness. You have witnessed the violence of supernovae that forge heavy elements and scatter them to space. You have felt the presence of dark matter, invisible yet essential, holding everything together through gravity's patient pull. You have learned that spiral arms are not fixed structures, but patterns flowing through the disk, that stars migrate far from their birthplaces, that the galaxy is not static but constantly changing, growing, evolving. You have discovered that most of what exists is invisible. Dark matter outweighing visible matter many times over, neutrinos streaming through everything unnoticed, magnetic fields threading invisibly through space, gravitational waves rippling through the fabric of reality itself. The universe reveals itself in many wavelengths, many forms, most of them beyond direct human perception. You exist as part of this vast structure, not separate from it, but woven into it at every level. The atoms composing your body were forged in stellar cores and scattered by supernova explosions. The oxygen you breathe was created when massive stars fused helium nuclei together, then released when those stars died. The carbon in your organic molecules, the nitrogen in your DNA, the calcium in your bones, all came from stars, cycled through the interstellar medium, eventually incorporated into the molecular cloud that formed the sun and its planets. You are made of stardust in the most literal sense. Not metaphor, but verified fact, confirmed by nuclear physics and stellar evolution theory and spectroscopic analysis. Every atom in your body, except the primordial hydrogen, was created in a star. You are the galaxy's children, assembled from its scattered matter, animated by energy that ultimately derives from fusion reactions in the sun, itself powered by processes occurring in all stars across the universe. Tonight, as you rest, the galaxy continues its ancient dance. Stars are forming in molecular clouds, new suns igniting for the first time, planets condensing from protoplanetary disks. Other stars are dying, red giants shedding their outer layers, massive stars collapsing in supernova explosions, white dwarfs cooling slowly toward darkness. Rogue stars race toward the galactic edge at escape velocity. Hypervelocity wanderers drift through intergalactic space. Ancient metal-poor survivors carry memories of the universe's youth. The Milky Way turns on, differential rotation creating spiral patterns, density waves compressing gas, star formation lighting up the arms in curls of blue and white. Dark matter holds everything together through invisible gravitational bonds. Magnetic fields thread through the interstellar medium. Cosmic rays stream through space. Neutrinos pass through everything. Gravitational waves ripple outward from distant catastrophes. And you float within it, a small warmth in the dark, resting in the spiral arm of a quiet, radiant sea. You are not outside the cosmos looking in, but inside, participant rather than observer, made of the same material following the same laws, subject to the same forces that shape stars and galaxies. The iron in your blood was forged in a supernova. The oxygen you breathe was sculpted in stellar cores. The calcium in your bones came from massive stars that died billions of years ago. You carry within yourself fragments of the galaxy's history, atoms that have been cycling through space for longer than Earth has existed, building blocks older than the solar system itself. In this sense, you are ancient. Composed of material nearly as old as the universe, temporarily organized into complexity, but fundamentally continuous with everything else, not separate from the cosmos, but a particular configuration of it, one temporary arrangement among infinite possibilities. The galaxy dreams itself into being through you. In your consciousness, the universe becomes aware of itself, matter organized into patterns complex enough to contemplate its own existence, to wonder about origins and meanings, to ask why there is something rather than nothing, to sense the profound mystery of being at all. You are the galaxy looking back at itself, atoms arranged in specific patterns that can think and feel and wonder. The cosmos examining its own structure through the temporary lens of human awareness. In you, billions of years of cosmic evolution have produced something remarkable. Self-reflection, consciousness, the capacity to understand and appreciate the vast processes that created you. This should inspire not loneliness, but connection. You are not isolated from the universe, but intimately part of it. Not foreign to the cosmos, but native to it. Born from its substances through its processes. Existing as one of its possibilities. Thinking its thoughts through your neurons. Feeling its presence through your senses. The night sky is not distant scenery, but family portrait. Those stars are your cousins, siblings from the same cosmic lineage, made of the same materials through the same stellar alchemy. The Milky Way arcing across dark skies is not separate from you, but the visible trace of the structure within which you exist, your home on the largest scale, the community of stars and gas and dark matter within which everything you know resides. Rest now in the cosmic embrace. So rest now, gently, knowing where you are and what you are. You float in space on a planet orbiting a star in the spiral arm of a galaxy containing billions of suns and trillions of worlds. You are composed of ancient material cycled through multiple stellar generations, temporarily organized into the complex pattern that is you, conscious and aware and capable of wondering about it all. The galaxy turns around you, slowly, majestically, its spiral arms trailing through space, its stars orbiting the center in differential rotation, its dark matter halo extending far beyond the visible edge. Silent orbits continue. Light travels. Stars are born and die. The great recycling continues, making and unmaking and beginning again, and you are part of it. Not a visitor or observer, but a participant. Not separate from cosmic processes, but created by them. Not watching the universe from outside, but experiencing it from within, as one of its manifestations, one of its possibilities, brought into temporary being. Let this awareness settle over you like starlight, gentle, ancient, connecting you to everything. You are home. You have always been home. The universe is not elsewhere but here, now, in you and around you, interpenetrating everything, making everything possible, including the miracle of your existence. Sleep well, child of stars. Dream softly in the cosmic night. The galaxy holds you in its gravitational embrace, spinning you through space at hundreds of kilometers per second, yet you feel only peace, only stillness, cradled in forces you cannot sense but which never release their hold. You are loved by gravity. You are warmed by fusion occurring in the sun's core. You are protected by Earth's magnetic field, by the atmosphere, by the heliosphere, by nested layers of shelter, allowing you to exist in comfort within an environment that would otherwise be instantly lethal. You are held by the Milky Way. Not personally, not consciously, but physically, gravitationally, genuinely. You are part of its mass, contributing your microscopic fraction to its total, bound to it by forces that will never release you in your lifetime or a billion lifetimes. Rest in that certainty. Rest in that belonging. Rest in the knowledge that you are home in the deepest sense, not just on Earth, not just in the solar system, but in the galaxy, in the universe, in the grand structure of reality itself. You belong here. You have always belonged here. And as you drift towards sleep, the cosmos continues its ancient rhythms. Stars forming, orbits proceeding, light traveling, darkness holding everything gently in its vast embrace. The Milky Way turns on,